Did anybody else have trouble getting on the Zoom? I just heard Michael just posted that he was having trouble finding it.
Yeah, Matthew, I had to copy and paste the link. I don't know if the link works.
Huh. Yeah, let me double check. Well, it is the right link. Okay. Oh. Doo-doo-doo. Okay. Well, maybe we'll wait a couple minutes in case those people find their way in. How's everybody doing?
Pretty good. How are you doing?
Doing pretty good.
Doing okay.
Right. Hey, who is this?
Michael Sater.
Hey, hi, Michael.
I see you're registered for the Brooklyn meetup.
Yeah, yeah,
Are you able to connect?
yeah. I'm connected right now.
Oh, you might have to go through the email.
Connect. It's telling me it's an incorrect URL. Send me your URL. Do you have that?
I'm going to send you my URL. No problem. One moment.
Yeah.
Can you hear me?
The calendar page didn't do it correctly. It had a bad URL.
That's so weird.
Matt, can you hear me?
Yeah, I can hear you.
Okay. Yeah, it was, it didn't work for me either.
Huh?
But the email URL was correct.
Okay, okay.
That's how I got here.
That's so strange. I mean, I look on the page and I this part is like the right URL.
Michael?
Yeah.
I clicked on the app, the link from the app, the Meetup app, and then it worked.
I just sent you the URL in an email.
Hi, this is Siddhartha. I first time in this meetup, but I just wanted to say that the link on the meetup page, like that, if I click on it, it doesn't work. And then it says open the app and then it works.
Okay.
Not tomorrow.
Huh. You know, I didn't do anything different than I normally do, so it's interesting.
Yeah.
There's a problem. Maybe Meetup changed their Zoom policy or something.
Michael Fishbein was missing this last week, and he's come back and he looks very shifty.
I confess that I've used a different piece of hardware every time I've joined this thing. Like installing Zoom and the whole, and this is the time I'm on my phone. So
Okay.
My experience has been that if I miss the opening moments, I might have to wait 20 minutes to get accepted. So I was eager to and before even figuring out
you're walking about in the Blair Witch Project. So.
Yeah. All right. Ooh,
the Quantum Witch Project is what it is.
All right. Well, I think we should get started. So the first thing I wanted to mention today was I put together a bibliography. Some people were asking last time about the origin of, the Majorana polynomial representation of spin, the extent to which I was, adding new results or following, already existing stuff. So I had this huge folder on my computer of all these papers and stuff like that. So I finally put up, if you go on the site at the bottom here, there's this link to bibliography. And I put this big, in construction logo here because, before war and the formatting of these citations is totally screwed up. I just was like copying and pasting stuff from these papers. So, beware. But for example, here, you can see many papers on, the Majorana representation, both, background papers or papers that attempt to derive it in various ways, and papers which use it for stuff. For example, this one is kind of interesting. A paper by Jason Zimba and Roger Penrose, where they use the Majorana representation to prove some interesting things about contextuality using, polyhedra on like the Riemann sphere is kind of interesting. I really recommend this book, The Geometry of Quantum States by Ingmar Bengtsson. It's a fantastic book and goes into a lot of the detail. Various things like this one, some properties of coherent states is great. Coherent states in quantum physics. A lot of these are cool. And these like essays by Nicholas Wheeler are also great. You can find those online. I will be updating this. Oh yeah, and you can see here's Majorana's original paper. This paper by LaBeouf. It's actually, I said it's from the 70s last time. It's actually from the 90s. This one, I sort of took a lot of the, where you derive the equations that govern the individual evolutions of the stars. I followed the exposition fairly closely.
So clearly you read and studied all 311 essays and books before our last meeting.
Well, I tell you, I've been interested in this Majorana thing for a couple of years now. I first discovered it at the, end of like 2017, beginning of 2018. And it's just sort of been in the back of my mind. So over the years, I've collected, many of these citations. And
Matt, did you say that the links that you showed us are at the bibliography section?
Yes.
It's all part of one section. Oh, okay.
Yeah. You head down here.
Are these original? Those links are some of them your original work?
No. No, this is all other people's stuff. Yeah. I have not published a paper in a physics journal.
No, because I think the last time you posted some links, some of them were yours, weren't they?
I don't know. I'm not sure. I'm not sure what you're referring to.
I was wondering if before, because what you do is always intricate. You're beguiling a Zoom room full of physicists here every day, or even though you've not studied physics formally in grad school. But I was wondering, in terms of since this portion of your presentation sort of began with the issue of spin, I don't think we really ever discussed what spin is. We have this elegant mathematical model, and we have your attempts to establish a foundation for it by with the metaphor of pebbles for whatever the indivisible atom of Greek atomism, and then a series of systems of number that comment on or supersede the previous level, so you've got layer on layer of foundation, of mathematical and possibly logical foundation to what you're doing. On the other hand, we do not know what spin is.
Could you repeat that, Victor? Oh, no, never mind. Never mind.
No, thank you. Yeah,
We do
question.
not know what spin is. So we have this analogy to the classical realm, to the realm of angular momentum, right? And there's the distinction between orbital angular momentum and spin momentum. You might call it axial angular momentum, and it seems to be closer to, you know, axial angular momentum. Some call it intrinsic angular momentum or total angular momentum, some of the physicists who describe it. And what we have is a mathematical model to a certain degree of angular momentum from the classical realm, the mathematics of which can be applied to a set of behaviors in the quantum realm. But we don't have any verification of whether what we're talking about is a particle with wave-like qualities, a wave particle or particle wave, a wave with particle-like qualities, or a wave that is just an oscillation or an excitation in a quantum field. Or is
Victor,
perhaps...
it's a magnetic property of matter. That's all it is.
Well, it's a magnetic property that we have a mathematical model for, and that we have measurements for, incredibly simplified measurements of up, you know, spin up and spin down, right? Just because something in the initial experiment in the 1920s got distributed slightly above the horizontal or slightly below the horizontal. One is spin up and the other is spin down. So what we have is a very primitive observational view and an incomplete observational view. And this declaration of the existence of spin, I'm not saying it doesn't exist. I'm not saying it doesn't work in every way, you know, for, you know, to measure things experimentally. But I'm saying is we haven't the slightest idea what it is.
If I may just say, I think it's like asking what charge is, or any other kind of fundamental property. It's one of those fundamental aspects to particles. You know, they have a mass, they have a charge, they have spin, and so it's.
But is mass really? Just for a second, I don't think mass is a fundamental quality of matter or of what we call particles or
well, then let me
particles.
just say charge then.
Matter, like mass is not there shortly after the Big Bang. It does not begin until you have the Higgs field, and then
Victor,
it is not.
Victor,
and then most of the mass comes from the strong interaction from the most recent thinking. Therefore, it's not intrinsic to matter, and all of these properties that we're talking about, even this supposedly simplest one, mass, are we describing them correctly with language that is descriptive, narrative, logical, with symbolic logic, with mathematical logic? Are we?
Victor,
I would say maybe charge is safer than
energy. Mass is energy, and in quantum field theory, mass, material particles are excitations of an energy field. Mass is energy, E equals mc squared.
You're using parts of a later definition to define something. I'm talking about
mass. Maybe has a messier picture to have to think about, but charge I think is pretty clean, and spin is kind of like a magnetic version of charge, but it has two values, and you can always query the system.
There are
which of the two values.
There are certain properties of, let's just call it matter for argument's sake. There are certain properties of matter that nobody really understands what their fundamental nature is. We accept them. Charge, energy, so on and so forth.
Yeah.
I think in the, you know, to get at the, you know, the underlying question of, you know, why spin? I think that, you know, I'm going to have to defer a little bit, you know, insofar as like I'm trying to build this up somewhat like progressively. You know, eventually we can talk about, you know, when you get to like relativistic quantum field theory, you know, the spin plays like an important role in like the consistency of the equations. You know, as a justification, I feel like, you know, we're not going to be able to sort of elaborate that out right now because, you know, in a way we haven't gotten there.
There's also
Dirac's
this little
equation-
issue about spin, this little issue, which is immense,
Yeah, so
which is
so
that based upon the size of the particles as we understand them, this
Yeah, like-
spin would have to exceed the speed of light for the
Yeah.
math to work out. This is a very,
Yeah, nothing's actually spinning.
That's true. And so the idea is like,
very
you have
minor issue.
yeah, they
That's
call it,
why you can't describe it classically. It's a quantum phenomenon. What you said is correct. The atom would have to spin fast, or the electron would have to spin faster than the speed of light. That's why we only analogize it to a classical concept with which we're familiar. But it is a quantum concept that nobody at this point really understands what it is. You just have to accept it as a magnetic property of matter. And it either aligns or it disaligns with the magnetic field. And that's all it is.
yeah, the surprising thing is that, right, and like the reason it's called like a form of intrinsic angular momentum is that, you know, each, you know, spin, like a spin half or spin one, I mean, it's always rotating or spinning at that total angular momentum.
But it's not really spinning. Spinning is just a classical analogy that we use.
Yeah.
You know,
But it ends up having units of angular momentum.
Yes,
it-
and it does
yeah,
add,
it
does
deserves
add to the
reputation of-
angular momentum. In an atom, the spin does add to the orbital angular momentum.
sure.
So
Yeah.
we know it's the same kind of thing, but exactly what it is, nobody knows.
And so far, we've been treating the spin completely independently of everything else. Like, is it a spin of this, of that? We don't care. You know, we haven't been describing, you know, the position state of a particle. We've just been treating, you know, the properties of like a spin state itself. You know, if you have a particle, like the spin is going to be tensored to the position wave function and so forth. And, you know, we're about to go into a little thing about the Stern-Gerlach apparatus. And I have a model where you can, like a very simple coupling between position and spin that we'll see. So yeah, like I'm gonna defer the question about, you know, ultimate nature of spin. Because yeah, it's, you know, there's a degree to which it does not correspond to our classical concept of a spinning particle. There's all these sort of funny things. You know, I mentioned at the end of this section, the matrix section, some of these things that were just brought up, you know, that, you know, relativistically, this was a classical object and it was spinning, the surface would be spinning faster than the speed of light. Like another thing that makes it different from a classical particle is the phase, you know, the, you know, fermions, when you rotate them 360 degrees, the wave function goes to the negative of itself. And for bosons, they come back to themselves. And so there's like this extra way that a spin state transforms under rotations, which can be somewhat, you know, visualized using the classic, you know, Dirac trick or whatever. So yeah, there's definitely some trickiness.
When you get to the end of the matrix section, is Morpheus going to show up?
Yeah.
What was that trick by Dirac?
Oh, so, you know, if you have, you know, imagine, you know, like I actually have water in the
So the
slide.
one with the belt? You can do it with the belt.
So, you know, I can
Okay.
do this thing, right? Kind of like rotate it, but then I can like undo it. Oh God, without spinning the glass.
Non-commuting operations. Yeah.
Yeah, so like the first thing's like you know, one 360 rotation, and then another 360 rotation, and then
I didn't know that Dirac
3D space without spilling the glass.
did that. I bet he dropped the glass a bunch of times before he got that one right.
This is what Feynman had in his book, right? This same example about the waitress like rotating that plate.
Yeah, I learned it.
Yeah, sure.
Fine.
And you can see an interesting example here. It's sort of a property. If you put like attached strings to like a cube, you can see that they, this thing can rotate without those strings ever getting tangled up.
It's cool.
And I think that's, I don't know if this is the best way of thinking about it, but you know, I kind of imagine it like these are like the flux lines or whatever, you know? And it's like they just don't get tangled up. And that's sort of why.
Wait a minute.
Sort of imagining that the I don't know if that's exactly, you know, accurate literal interpretation of this. But it's an interesting property of three-dimensional space that these strings don't get tangled up.
It's all made possible by the flux capacitor.
The flux capacitor. Okay, so, and okay, I'll say this too. So, you know, I added a lecture I wasn't originally gonna do for next time, where we're gonna go into a little adventure into the theory of loop quantum gravity. And there, the sort of representation theory of spin is used in a different way in order to quantize little chunks of space. In other words, the spins come to represent instead the areas of quantum polyhedra that are like glued together into a big chunk of quantum space. And there, you know, the mathematics gets, you know, yet another kind of interpretation.
That amplituhedron?
It's not related to the amplituhedron other than the fact that, yeah, they both involve convex shapes. So in a way.
But it's not part of what Arkani Hamed has been excited about.
No, no, it's a different subject.
Okay.
But perhaps related. All of which is to say, you know, we don't have a finished theory of quantum gravity. We describe, you know, a particle, you know, in normal theory is just, okay, like a spin state tensor to a position state. But, you know, what if we can't take that position state for granted and stuff like that? So we'll get into that more next time. So just a quick review about, you know, the Stern-Gerlach apparatus. You know, you get a spin. You know, the experiment was originally done with silver atoms. And yeah, as we've been saying, you know, it travels through an inhomogeneous magnetic field that's like stronger above and below, and comes up either here, it's detected, or it's detected down here. And there's this correlation, which is that the spin was detected up, then the spin state is aligned, you know, up with the magnetic field it went through. And if it appears here, then the spin state is down. So there's a kind of entanglement between the position and the spin. You can see here, you know, the original.
Hey, one moment, when the experiment was first done, did they know that the spin was up or that the spin was down? Or did they just notice that the atoms get split into two patches?
Right, so.
I believe the latter.
Yeah, so if you, you know, instead of measuring like the position per se, if instead you kind of let, say, like the top beam go through another Stern-Gerlach apparatus, you know, you can see that it gives results consistent with it being up relative to the field that it went through, and so forth. So, you know, you could again, I mean, you're still measuring you're getting the spin as you know, you're measuring the position as a proxy for the spin.
I think it's historically, I believe historically that it was a surprise to see two spots instead of like a continuous line.
They would have expected either because of the charges neutralizing themselves. They tried to choose atoms that would be as totalities neutral, that it would simply pass through unaffected through the magnetic field, or that there would be some kind of scattered distribution, and instead it was this very clear up-down distribution, which was not foreseeable unless if they already understood what we might or might not understand at this point about quantum mechanics.
I don't think that they, like, spin was predicted to be quantized and then they confirmed it. I think it was, you know, realized by seeing two concentrated spots.
That, I believe, drove this discovery.
Matthew, why did they call it spin half instead of spin 1 up and down, or spin 27?
Well,
to make the difference.
You know, they're the different, you know, eigenvalues of the total spin operator, and the half integers come in because you're using not the normal sort of group of 3D rotations, but it's double cover SU2.
They're using
And that gives you
it's
that
the
sort of thing.
Planck constant. It's the Planck constant that creates the
Right. Yes,
integer
of course.
spin or the half integer spin.
So they didn't call it spin half until they related it to SU2. Is that what you're saying?
Well, I think that there's another thing, which is that you got this angular momentum algebra, but basically you have this operator where you can like transform a spin up to a spin down by applying a lowering operator, which just in general lowers the spin value by 1. For any spin system, there's like generic operators, and so if you only have 2 and one is going to be one thing and one is going to be the other, and this difference is going to be the integer 1, then to have one be up plus and one be minus, you got to have plus 1, because if you have like 1, then it's 1 0 minus 1.
So they knew it had to be lowered or raised by a unit, so therefore it had to be half integer.
That brings up another issue about your visualizations. Maybe I was misinterpreting them, but since a spin up or spin down is just determined by any possible angle below the horizontal in the experiment. In other words, it could be in absolutely any direction toward the downside or toward the upside, and it's spin up and spin down. So you end up with this very primitive up-down distinction. But you had this complex series of, in some of your visualizations of vectors, and they were altering direction. So what were you implying by that in relationship to the notion of spin up and spin down?
Yeah, great question. So the picture of it where it's just an arbitrary constellation evolving is like a picture of the isolated spin. When you do the measurement, it's like, for the spin half case, the 2 up and down states are just like these 2 simple constellations. In the spin 1 case, it's, the 3 possibilities are, eigenvalue 1, 0, and -1. And in terms of constellations, they correspond to, 2 stars at the North Pole, and then, 1 star at the North Pole, 1 star at the South Pole, and then 2 stars at the South Pole. So, these, they're these sort of, these are going to be like the basis states of, say,
-1, 0, and 1, or
yeah. You can think about each star is contributing an angular momentum of 1/2. So clearly, this is like 1/2 plus 1/2. That's 1. This is just 0 because 1/2 minus 1/2, and this is 2 negative halves.
Matt,
let me try to do some reverse engineering here. I was not present when this experiment was done, of course, but one way of guessing what happened is the following. Once they got the results of this experiment, they realized, we have 2 distinct quantum states here. They knew that in quantum mechanics, you have Hamiltonian, you have some operator. The operator is different states, they're discrete states. And this noticed here, we have an operator that has 2 discrete states. What kind of symmetry group is going to give us 2 eigenvalues with 2 distinct eigenvectors? And since they were very good in mathematics, they said, SU3. SU3 is going to... SU2, yes, sorry. So SU2, SU2 is going to do the trick. SU2 in the
and particularly as that the Hamiltonian that describes the field, you have to be able to rotate that Hamiltonian in itself. In other words, we can orient the Stern-Gerlach apparatus, in any way we want in 3D. And so,
But Matt or Moshe, historically, who came up with spin half? Was it? I don't think Stern and Gerlach were aware of SU2.
I believe
Pauli.
Was it Pauli? It was
I
Pauli,
believe it was
right?
Pauli. Yeah.
Okay.
Even before the relativistic theory of the electron was developed.
So Stern and Gerlach just realized that there was a quantized characteristic,
Yeah.
a magnetic characteristic.
Pretty sure it was
But
Pauli.
Pauli
This is
explained it.
1922. This is before
Yeah.
even the Schrodinger equation.
Pauli has his name all over spin stuff, but I think marrying it to quantum mechanics more generally was Dirac's theory of the electron.
Well, Dirac's equation, you derive spin half from Dirac's equation, which
Yeah, that's what I was sort of
which
alluding.
makes Dirac's equation valid in a certain sense. But this was all known before Dirac's equation.
So in a later meeting, hopefully we can talk about like that. But like, let's leave that to the
Even before Dirac joined special relativity with quantum mechanics in his equation, Schrodinger had attempted to do so and despaired because it wasn't working.
Yeah.
And so
It was actually Klein-Gordon. Schrodinger came up with what we now call the Klein-Gordon equation, and because it had negative probabilities and negative energies, he threw it out. But then it was reinterpreted by Klein and Gordon. But Klein-Gordon is for bosons, for integer spin. Dirac's equation is for fermions, half integer. But one of the great things about Dirac's equation is that it naturally, mathematically, comes up with that the particles are half spin.
Yeah, it's a beautiful thing. So like let's get into this little thing about tensors now. Okay, so contextualizing this in the context of our unfolding story about different kinds of numbers. We've left the world of matrices behind, and now we're going to enter the world of tensors, or multilinear transformations. And metaphorically or analogically, or however you like, we can look at this as a kind of coexistence of a bunch of matrices, coexistence of linear transformations, a multilinear transformation. So far, when we were working in the matrix world, matrices gave us perspective on vectors. In the quantum case, what was interesting is that each matrix was associated to a certain experimental situation, like, measuring the spin in the x direction or the y direction. And its eigenvectors provided a basis for the outcomes of those experiments. And so we could expand a given state in this basis of, call them like experimental outcomes. We used complex vectors in unitary matrices specifically so that the components of our vectors can be interpreted in terms of probability amplitudes for those outcomes to experiment. Each matrix provides a kind of metric, a different way of assigning weights to outcomes, leading to statistical expectation values for a given observable. And the relationships between experimental situations, like for example, measuring an X versus Y versus Z, is encoded in the algebra of the matrices. And they implement the relevant symmetry groups. And the interesting thing was, like, despite like this talk of probabilities and outcomes and blah, 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 we can still form a kind of definite geometrical picture of this quantum system, using the constellations, even as, like, almost from like a dual perspective, the very same geometry can be interpreted in terms of statistics. When we considered, say, a single spin half, evolving unitarily under the Schrodinger equation, we seem to explain away, at least at first, the mystery of superposition when we realized a perfectly definite constellation, a point on a sphere, can be written as an arbitrary sum of orthogonal basis constellations. So,
I'm sorry, you were muttering. An arbitrary what?
Arbitrary sum of orthogonal basis constellations.
Okay.
So that, to say a spin is in a superposition being up and down the Z direction, it sounds kind of mysterious because we're using the language of outcomes to experiment, but it's really no different than saying the spin's pointed in the X direction. Because any point on the sphere can be written as a complex linear combination of two antipodal points on the sphere, which fix an axis. And in the experimental case, that axis corresponds to the, direction of the external magnetic field.
Matthew?
Yeah.
Matthew, can you let me in again on a different computer? The computer I'm using right here is giving me a hard time. So just let me know the other one.
Yeah, I just did. So Furthermore, when we were just considering an isolated spin evolving under unitary evolution, we came up with this kind of cool, like classical picture where these special points, the Majorana points, were kind of like particles confined to the surface of the sphere, moving around under the influence of forces like generated by each other. And so that was cool. But now we have to consider a not isolated spin, a spin which is gonna, maybe it's measured, maybe it's gets entangled with things. How does the picture change? Can we still maintain this sort of nice, satisfying classical geometrical picture of the spin, etc.? So, so now we're gonna talk about measurement, right? Like the first naive way of thinking about measurement is that it's like a filter. It's like a situation that slices something up in a certain way, giving weight to different parts of it, so that, because of the particular orientation of the spin relative to the magnetic field, maybe only the up part gets through with a certain probability. Maybe the down part gets through with a certain probability. So the first, you might say, surprising thing about the Stern-Gerlach experiment is that it hadn't seemed that a particle just zipping through a magnetic field was a filtering operation at all. We're familiar with, you send light through a prism and it gets split into different beams. I don't know if anyone had expected that, angular momentum could work in a similar way. You send a spin through a magnetic field and it's kind of like it splits into a bunch of beams of different angular momentum, like light being split into separate beams by a prism. So the first surprising thing is that that should be the case at all. And it sort of makes you ask, well, what is exactly the nature of this filter? But you can't necessarily look at, so now we're going to talk about sort of the paradoxes of viewing the act of a spin going through a magnetic field as a filter operation, interpreted kind of classically. So what really goes on, as I was alluding to before in a Stern-Gerlach experiment, is, we don't measure the spin directly. We actually deduce whether the spin was up or down by measuring its position. So if it ends up along over here, that implies the spin was up, and if it ends up over there, that implies the spin's down. And so what the setup is doing, is entangling the position and the spin. So I have here just like a simple little visualization, very simplified model of a Stern-Gerlach setup. It's going to be only in 2 dimensions, and the particle is going to start on the left, and it's all right. Well, let me boot it up. I'll just show you what it does before I explain.
It looks very simplified.
Yeah, well, so we don't treat.
I'm only joking. I'm only joking.
We don't treat the multiple dimensions. We just, you'll see what I mean. All right, so let's start with a spin half.
Victor, how's that bird doing? Did you torture it?
That bird. Okay, so here's the spin. It starts on the left, and you see as time goes on, okay, see how this dude's getting bigger here? Okay.
What's happening?
All right. Now,
what does that mean?
Now I'll explain. All right. So there's a grid of positions, and the size of each of the spheres represents the probability for the particle to be at that position. And supposing the particle is in that position, it's going to be found in a certain spin state. And that is the spin state that you see given by the arrow within the sphere. Now I'll run it again. We start with a spin in the up direction. Okay, very simple thing. So it starts on the left, and as time goes on, the probability spreads out. And then you see that right here, there is, as time goes on, there's a state which is an up state, which gets really big. in this position. All right, so now watch what happens when I change the spin state that we start off with to be a spin down state. Oh shit.
Still see spin up.
Yeah, sorry, I changed it in the wrong file. Okay, boom, boom, boom. All right. Yep, so now it starts in the spin down state, and we see the same dynamics as before, and lo and behold, oh, this guy's coming up, spin down, look, all the probability concentrated right there, okay?
And just going from left to right,
Yeah,
what does that
so it
represent, these
starts on the
columns?
left, it has a momentum that's taking it to the right, and then its sort of up-down position is coupled to its spin degree of freedom. I'll show you the Hamiltonian in a second. Before we get there though, let's now look at like just a random linear combination of up and down. So now here, the spin's just going in some random direction. And we wait a little bit. And we're gonna see basically, you know, in this case, it was mainly up or whatever, but you see there's like a little bit of stuff going down there. You know, you gotta do it a couple times to really get a nice.
I'm sorry, I don't know what I'm looking at here.
Okay.
Like where's the stern girl, like where's is the source coming from? It's going into the board or like coming from the left?
Yeah, wait, let me, okay. I should have added some like little, make this a little more sophisticated. So yeah, so we got this world here. Spin starts off in a certain state. And the idea is like, oh, there's a magnetic field, you know, in this like Z direction. And this guy, you know, is gonna go over here. And then, you know, it's gonna be like, maybe, you know, it's gonna be up, a certain amount, and it's gonna be down a certain amount. And the idea is that the size of this guy is gonna be like the probability, and the size of this guy is gonna be the probability of it being down. So the particle has a momentum, it's traveling in this direction. There's this magnetic field like this, and that acts on the, and so the spin degree of freedom gets coupled to the position degree of freedom. So you'll see here, if you just look at the Hamiltonian.
Well, on that diagram, could you just add some sort of features that resemble what we just saw with your graphic, movie? How do I relate that?
So yeah, the idea is like this whole space is gridded up into locations. We're considering a kind of like discrete approximation.
Yep.
And then, you know, looking at the probability for the spin to be at each of those locations.
As a function of its position, like as it's moving along, those probabilities are changing? Like as it's getting closer to like
so
the
as
middle?
this thing evolves at, so I'll do it again. Like I chose another random.
Because like, I guess like a simple trivial case, if it's spin up to begin with, then why isn't there anything other than just spin up dots not changing over time? Because it's predetermined what the probability should look like.
I'm sorry, say the question again?
I just, like if you have a spin up coming in,
yeah,
spin up in the Z direction, why is there an evolution of the probability over time? But
good point.
Why are the dots growing or shrinking or whatever?
Right, so what the Hamiltonian does, here it is. So there's just a little momentum in the X direction here, okay? So that's what this term does. It's just going along in the X direction. Then we have this term here, which couples the momentum in the Z direction to the spin Z operator. So that the state of this thing is a tensor product of its spin and its position. And then we have this term here, which is the magnetic field acting on the spin. So there's three components to this Hamiltonian, basically. One is momentum in the X direction, that's just going along, you know, independently of whatever. Then, again, it's a simplified model. And then you have a coupling between the Z, the up and down position with the spin. And then you have like the magnetic field evolving the spin itself. So this is like the dynamics of what's going on like in the experiment, basically. So, you start off with the spin all the way to the left. And then as it evolves in time, it ends up that you then look at sort of like a slice somewhere, and you can see the probabilities that the spin ends up at those different locations here represented by the radius of the sphere. And if it's in that position, it's going to be in a certain spin state. And that's the arrow that you see. And so let's do the example, maybe it'll be easier
Can
to
I ask you a question?
spin
You know,
right.
this, can anybody hear me? Can you hear me, Matt?
Yes, yes.
This is according to the Copenhagen interpretation, not according to the Bohm interpretation. Let me ask you, why should we consider which direction the particle goes as a quantum phenomenon rather than a classical? In the sense that if it has a tendency to already be pointing in a certain direction, why would it not continue in that direction? And of course, probabilistically, half the particles would have a tendency one way and half the other way.
Yeah, I mean, let's come back to that. I mean, I don't have anything smart to say about that. So here, we're considering a spin 1 particle in the 1 state. So now the idea is that here we have all the probability concentrated along the up path, and indeed we see this little guy is up. If we change this to, say, the 0 state of the spin 1 guy, here, you see the arrow is just, a point in the center of the sphere. And we get that all the probability is concentrated here along the middle path. And if we, at last, do the spin -1 state, then we'll get all the probability concentrated down the most low path over here. So those are that's what the basis states do. But as I'm saying, if we just choose a random spin 1 state, then it's going to be a superposition of being in those 3 locations. So here we had this random guy. And we see that, yeah, it was like mainly spin 0, a little bit spin -1, not really much spin 1. So you see what I mean? Okay. So the point I want to emphasize is that, what's going on in this experiment is a coupling between the spin and the position. Okay?
Are you aware of the fact, in terms of this coupling, in terms of this entanglement, that they have now imaged for the first time in 2019 entanglement, and you can actually see it as a kind of a probability distribution, but that is actually real, and that is that can be made into, it can be telescoped temporally, or that you can see it as the position of the particle in each instant. Have you seen this visualization?
No, yes, send it my way.
It's 2019.
Do you recall
Okay.
the name of an author or anybody, any keyword to search?
It was, I'm not recalling who, was it the UK? I'm not recalling, but if you just do, if you go 2019 photo image of entanglement, it's the very first time that it's been done.
Okay. I mean, my intuition there is, you can see an image, but I mean, entanglement is like, I mean, it's not.
It all matters what they really mean when they say.
Yeah, I mean, it's just like, you're not gonna be able to visualize it per se.
So it's a very, very clear visualization. It looks like basically if you see it individually, you start to sense that you're looking at a probability cloud. But as they telescope it temporally, what you basically see is a ring that is not quite joined at the center. There's a certain degree of darkness there, and it has a very, very clear shape to it, which is determined by the number of times that the particle appeared in a certain position. It's fascinating to see.
Yeah,
it's the very first time.
Yeah, I mean, one can talk, however, it should be noted, about entanglement between, arbitrary quantum systems, which like might not even have like a so-called position state, so to speak. Like, in other words, in general, you can't take a picture of entanglement. In the sense that, I mean, I want to encourage the view that like entanglement is a set of linear maps that take you from the state of one system to another system, and hence are represented by a tensor product. And that might lead to some consequences, say, in like the shapes of position states and stuff like that. But so in terms of the Stern-Gerlach apparatus, right, the spin and the position are being coupled so that, if we started out in a superposition of up and down, we end up in this entangled superposition of the particle taking the up path tensored to spin up, plus the particle taking the down path tensored with spin down, and the amplitudes are just like the original amplitudes of the spin. So then we measure the position, and then because of the entanglement, that steers the spin to be in a certain way. So if we measure this up position, then the spin was up, and so forth.
From July 13th, 2019, Science Alert has one that's with more elaborate imaging. It's scientists just unveiled the first ever photo of quantum entanglement.
Cool.
Science Alert, July 13th, 2019.
Yeah, send a link to the chat.
Thanks.
Okay, so if we were thinking completely classically, we would say something like, oh, okay, so for a spin, an inhomogeneous magnetic field is like a prism. It's like, it goes through, it gets split in a bunch of beams. There's nothing, mysterious going on here. When the particle goes through the magnetic field, it filters its spin, and so, only the up part or only the down part gets through with a certain probability. And then the field couples the spin to its position, and then so when I measure the position to be up, I can be sure that the spin is also up. But there's an ambiguity. We could imagine that this sort of collapse, this filtering operation, up or down, we're saying, oh, maybe it happens when the particle is going through the magnetic field, and then, whatever it is, up or down, then gets correlated with the position state. But there's another view, which is that, no, actually, we could regard the entire spin as getting through the magnetic field. And in fact, it ends up greater than when it went in. The relevant fact is that the spin gets entangled with position. So like in the tensor product space, you have these, 4 states, and the space of states is any complex linear combination of them. If the spin started in this state, then it'll evolve by the Stern-Gerlach dynamics into this state. The only terms that are there, those in which the spin and position are correlated, and the amplitudes are just the amplitudes of the original spin. So we could say, oh, no. The spin definitely, it actually comes out, both ways. And it's in a superposition of position states too. And then the collapse, so to speak, the filter happens when we measure the position. In other words, there's a kind of interesting trade-off here. We, on the one hand, could imagine the spin collapses to being up and down and is filtered when it's going through the magnetic field. But if we want to keep our mental picture of the spin and its constellation intact, we could switch to this other perspective, but then we have to view the spin as like being in two places at once, leaving the Stern-Gerlach apparatus both along the upper path and the lower path, the superposition of both. And then later on, when we measure position, the filter happens. And you're like, oh, well, how would you know? Well, there's a simple experiment. We could test it. In other words, why not join the up and the down paths? Like I'll draw it out. We want to know, where does the filter happen? Does it happen when it goes through the magnetic field? So we have a spin, splits into two beams. And how about, oh, you can't really see that at all. It's very, splits into two beams. Before, we were like, oh yeah, we'll measure the position, figure out what's going on. But what if we join the beams back together? We could just do that, whatever, some way. Just join the paths. And here's the thing, if you recombine the beams and then send this guy through yet another Stern-Gerlach apparatus, the results are just like you would never split the beams apart at all. In other words, the state that comes out is just the state that went in. So then we'd have to regard it as the spin took both paths. It exited the Stern-Gerlach along the up direction and along the down direction. And then those two states were brought together, and we recovered our original superposition exactly. In other words, you'd be like, well, okay, so then we can't look at the spin traveling through the magnetic field as itself a filtering operation, because you can undo a Stern-Gerlach measurement. Instead of measuring the position, simply create a way for the up and the down paths to recombine.
If I can ask a question, is that undoing sort of going back in time?
Sorry?
Is that when you say undoing, would you say like you can sort of go back in time and recreate like where we were to start with?
Yeah, in a way, yeah. So hold that thought. We're about to talk about decoherence, and I'm going to make a point very similar to that. Yeah, effectively, it's like reversing time. Although, in like the actual unfolding of the experiment, you'd be like, okay, it goes like this, and then we recombine it.
So picking up on what Sid just said, doesn't this violate causality?
No.
If we interpret it this way?
Well, I'm not sure.
Well, is it the case that there never was a splitting, just because it can be made to resemble having not split?
Yeah, why is this any different than just a mathematical excursion? This is not what actually takes place necessarily.
Well, I'm saying that you can do two different experiments. You can have a particle go through a Stern-Gerlach and measure the position. And then you could say, oh, it's up and it took the up path, or it's down and it took the down path. And we can regard the magnetic field as filtering the one from the other. But there's a different experiment we could do. Instead of measuring the position, we could recombine the beams and then do some Stern-Gerlach measurements on whatever comes out of that. And then in that case, we have to say that there was no filter at all. Both the up part and the down part went through, and we end up with the original superposition that we started with.
Matt, why is that not a classical experiment that you just performed? I don't understand the quantum aspect of this, except that you're introducing.
Well, because you're sending one particle at a time.
But you're only measuring the final outcome. So, of course, you're going to get the original situation. I don't understand how this is quantum in any sense. Why is it not classical?
The distribution is not scattered. The distribution is absolutely clear between up and down based upon the quantum phenomena, supposedly, of spin up and spin down. It's not a the effect is not neutral in spite of the fact that the charge is neutralized, and the effect is not scattered. And so this up-down distribution at the end of the experiment is a clear indication of the choice between up and down in the direction of spin.
It's no different from a double slit experiment. Like, this is just the double slit experiment, but like in terms of spin. In other words, if you have a double slit experiment, you have two slits, and a particle goes along, and there's two different experiments you can do, right? The one experiment is you could leave both slits open. The thing goes through both paths and leads to an interference pattern that can only be explained by the particle going through both slits.
Not according to Bohm, which is
according
what
to Bohm,
Michael's
exactly.
about to say. I could see his smile.
All right, just accept this for a second. Then the other experiment that you can do is you could ask right at the slits, hey, are you here or are you there? And then measure the position, and the interference pattern disappears.
Because you've changed the configuration.
Yeah,
Not because you made a measurement, but you've changed the
experiments.
macroscopic configuration. That's how Bohm explains it.
Okay.
So how do you relate this to the spin experiment?
But so are you saying that in addition to there being two possible outcomes due to just the pure spin, like a magnetic interaction, there's also this like effectively it's turning it into a two-path problem, and it's that they're always going to be highly correlated, the paths and the spin, but somehow I can't just think about spin.
Well, what I'm saying is that, what I said about recombining the beams is most often phrased in terms of the double slit experiment. You know what I mean? Like an introductory. It's like, there's two.
Right. Well, sure, but yeah, my feeling has been that the double slit is sort of it's a nice visual, but it actually has some subtle messiness to it in detail.
Yeah, sure.
But because they're not really
spin, I think
two states only, but anyway, but like the spin being sort of something that's known to be just up and down. There's
yeah, exactly. That's why I like it better. So you could what I'm trying to poke at here is this idea that classically it would make sense or whatever for if there's a filtering operation, some kind of collapse to one thing or another, it's going to happen like when the particle is going through the magnetic field, and so you could try to test that. And the answer is that whether you regard that collapse as taking place when it goes through the magnetic field depends on what later experiment you do. Just to draw it out again, it's like if I do this experiment where I just measure the position here or there, then if I get up here, it's perfectly consistent for me to say, oh yeah, the particle like went through this thing and only this part went through. Or it went through this thing and only this part went through. And so I'm like, oh, okay, makes sense. But there's a different experiment I could do that challenges that interpretation, which is that I can recombine these beams, and the thing that comes out, if this was just some random spin state, this will be exactly the spin state. In other words, I can only explain this result by imagining that this single particle came out of the Stern-Gerlach apparatus along the up path and the down path, and then those two parts of the superposition were recombined, leading to the original state. In other words, whether I regard like a filter as taking place or not depends on what I choose to measure.
Matt, why does this not violate causality?
Well, I think it's happening as a sequence of events. It's moving as time is evolving, it's moving from left to right. You know.
But he's saying the measurement determines the initial condition. That violates causality.
Condition. Yeah, the measurement that you choose to do restricts what you have the right to say about what happened in the past. That doesn't violate causality.
Of course it does, by any standard.
But what's the thing that's happening before it ought to?
So, I mean,
what's the incorrect order of events that shouldn't be possible if it's violating causality?
Yeah, exactly. Like the only thing that would violate it, you know, it's like sort of. Well, let's come back to that question.
The spin doesn't know beforehand what measurement you're going to make. So how can it decide? You know, how can it decide?
Michael, the spin is omniscient, Michael.
What's that?
The spin is omniscient.
Well, just Matt, is this? Do you have in mind basically the equivalent? Is this equivalent in your mind to the beam splitter for photons with that, and then they bounce off mirrors and the beams recombine?
Totally analogous. It's the same.
Okay.
Like, yeah, absolutely.
That's what you're going for, yeah.
Yeah.
Speaking of analogies, I just want to make one quick point. I said the last time, and you questioned what I was saying because you said that was polarization.
I may have spoken incorrectly.
Two places, the analogy made between spin up and clockwise motion and spin down and counterclockwise motion. Now, I do not even agree that we have ever genuinely described something which is, you know, genuinely analogous to classical spin. But if you simply think of spin up as the clockwise motion, if you reverse it to spin down, it becomes counterclockwise. You get a rotation, and so the analogy can be made.
Absolutely, and in fact, in 2 sections from now, we're going to see how we can, you know, model polarization using qubits and all the same mathematics of spin. And, you know, you're exactly right. I mean, that's totally true. And we'll have a cool visualization of that. The mathematics of polarization and spin are really 2 sides of the same coin.
So then you're passing this, let's say it were photons, you're passing this through a polarizer, and that's what's giving you the final result.
Yeah, something like that.
So it's a classical experiment. It's not quantum.
Well, you can do an equivalent 2-state thing with photons, which is you can use a beam splitter just by engineering the dielectric constants the right way. You can have it be that any photon that is incident on that material has a 50% chance of being reflected, 50% chance of being transmitted, and you can by angling that beam splitter, you can form 2 beams from an incident beam that way, and it becomes, you know, that splitting is a purely quantum.
Yeah, I mean, what makes it non-classical is the idea that one particle can be treated as being in 2 places at once.
I think the correlation, the correspondence between the position and the spin is really cool, and not something I thought of before here. I think it also it's not probably like the cleanest scenario to examine. I think there's like, you know, you could also say like at what point along the way it has the measurement, has like the splitting happened. You know, is it like it's based on the precision of your ability to distinguish 2 beams from one? You know.
Yeah, that's a good point. Yeah, so we're about to get to that kind of issue. So
yeah, so it's a little. There's one other thing I wanted to mention, which might also speak to this position relevance in the spin case, which is, I would think, like, what if you had the Stern-Gerlach apparatus sitting on like a detector that can like is sensitive to any movement of the apparatus itself, and so. I mean, this would, of course, require some ridiculous precision, but just theoretically, like if this, you can imagine like the whole box, you're not looking in, you don't see where it goes up or down, but if the whole Stern-Gerlach apparatus should recoil in, you know, one direction or the other, because in reaction to the electron pivoting up or down, you know, because there'll be some angular momentum from the you know, the arcing.
I like where you're going with that. Okay. Okay.
And it's, yeah. So that'd be I wonder
about that. Yeah. How to
because
analyze.
it's like if the thing moves, you know, that kind of, you know, might be argued to be evidence that it was split at the apparatus, but you know, I don't know. Might be some weird subtleties that make it unclear.
It's reminiscent of there. Yeah, there's like a thought experiment that Bohr came up
Or
with.
not, yeah, with the clock and the.
Yeah, with the clock.
Yeah.
Yeah, I know what you're talking about. Totally. Yeah, yeah.
Yeah.
I'll think about how to. Yeah, like maybe we try to like reproduce that argument in this case.
Yeah.
I'll have to think
Cool.
about it. So okay, but so here's the thing, right? Like so far we've considered, you know, got a spin, it's coupling to its position, and then, you know, maybe we measure that position. Maybe we send that spin through another Stern-Gerlach. Well, what if we continue this chain of correspondences? You know, the spin gets coupled to the position, which gets coupled to another quantum system, another quantum system. You can view this in some sense as like each time both states getting through and ending up at the end with, say, you know, if they're all two-state systems, a big ol', you know, product of, oh, that one being up, 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 plus that one being down, 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 down. In other words, if we measure the last one to be up, and all of them were up along the whole chain of causation. We measure the last one to be down, and all of them were down along that whole chain of causation. I'm imagining that like each step as the things get coupled, they get maximally, you know, so that all these states get end up in this sort of maximally entangled state. And what's interesting when you think about those states is that you could imagine the projection as taking place at any point along that chain, and you'll still get the same probability in the end. In other words, it's completely arbitrary where you imagine the filter takes place. We could imagine that, oh, the magnetic field did the filtering, and then the spin took one path, and then it took one path, and it followed it all up, and then it was up. Or maybe it went through the magnetic field in both directions, and then at that stage, the filter took place, and then, you know, it was up, and then it continued on and so forth. Because of the linearity of quantum mechanics, you know, it doesn't matter where you put the filter. You get the same end result. If any one of those systems down the line is up, then all of them are up, and vice versa for down. And this doesn't conflict with what we said before about switching up the experiment, you know, measuring the position versus allowing them to recohere. Before, we seem to prove that a spin must come out both exits of the Stern-Gerlach apparatus, therefore couldn't have been filtered by the magnetic field, since we could recombine the beams and recover the original superposition. But here's the important point. That's a different experiment. In quantum physics, like, you have to treat these different kinds of experiments as like essentially like different entities. In terms of the experiment we actually did, where we don't allow the beams to recohere, we're perfectly within our rights to regard the spin as having been filtered way back by the magnetic field, collapsing to up or down with certain probability, and then regard either the one or the others making it through no superposition over positions at all. But alternatively, we could do this other experiment, recombine the Stern-Gerlach beams. And if we did that, then we'd have to admit that at that point, you know, before that the particle was definitely in a superposition over all those positions and was taking each path of its journey all the way through.
There's something, this phrase of quantum erasing, like my sense is kind of like, you might be able to get away with saying that the beam did split, but because you engineered the apparatus to have these two paths converge again, you reintroduced an entanglement post and after, and going forward from there, you can't like the history of which beam it got split into is erased. I mean, that information is not accessible, you know.
Yeah. So that's totally relevant to what I'm about to say.
Matthew, I think I missed an important. Matthew, can you hear me?
Yeah, I can hear you.
I think I missed an important point. When you recombine the two paths.
Very hard to hear you, Moishe. You're
Yeah,
like
it's very hard to hear you.
reverberating and you're
Can you hear me now?
a little better.
Okay. When you recombine the two paths, two spins, do you get some sort of an interference pattern that you can detect?
Yeah, when you recombine them, the quantum coherence is preserved. And you can think about interference as being nothing other than recovering the original superposition of the spin.
But Matt, this can be
What
explained
about
classically.
how do you detect the interference?
Sorry,
With the double
very accurately. What was
With
that?
the double slit, it is very clear how you see the interference. In this case, how do you actually see the interference?
By sending the resulting particle through another Stern-Gerlach apparatus and seeing that it has the same state as the one that went in.
But Matt, this can be
No,
explained.
but you don't know what state it went in. If you send it to a Stern Gerlach and you recombine them, you have no idea what state it was to begin with.
So I'm imagining that I prepare a state that I know, and that's the one I'm going to send through the Stern-Gerlach apparatus. I now take both beams, and then I recombine it, and then I do, you know, this experiment a billion times, and I take the output, and I do like the normal Stern-Gerlach measurement on it. And from the XYZ expectation values, I recover the original state that I know went in.
Moishe,
And is the original state an eigenstate of the?
No, whatever it was. Well, it would be an eigenstate of whatever you know. I mean,
Matt,
But like if you started off in an eigenstate, then shouldn't you expect to only see that state be preserved until you measure off axis?
yes. Matt, you know, this can be explained classically. This is not a quantum experiment. This can be explained classically. Now, and
but
well, what the,
let's talk about decoherence.
I just want to let Moishe know this is the new Moishe, and we want to hear this Moishe all the time, because with his voice in the background as it is now, he sounds like Yahweh. And he no longer sounds like Moishe.
Yeah, like he's reporting from his lair.
He's gone beyond Moishe to right straight to Yahweh.
he is Yahweh. He's a Kohen.
So, okay, so we're going to talk about decoherence. Suppose we do the same experiment, but we imagine that we have, let's say, a gas of a bunch of red particles up here and a bunch of blue particles down here. I use different colors, sorry. So that when the spin, if the spin takes the up path, then it interacts with these particles and gets entangled with them and then continues on its way. But if the spin took this lower path, then it interacts with these particles and then goes on its way. What happens if we then recombine the beams? The answer is we lose the quantum coherence and we get a statistical mixture, which looks like the particle either took one path or the other path. So in the context of like the double slit experiment, if we how do I do this? Right, so the argument is this. Initially, if we didn't have, in say like the double slit experiment context, if we didn't have these extra gases here, these extra particles, then the two position wave functions associated with, you know, coming out the one slit or coming out the other slit are not necessarily going to be orthogonal. And therefore, when you add them together, they interfere. And because of that, you get the interference pattern. But here's the thing. If instead, taking the up path and the position state are also now tensored with the state of these like particles, these particles if it takes the up path, and these particles if it takes the down path, almost certainly those two states associated with going up and down are going to be orthogonal. Because almost all vectors in high dimensional space are orthogonal. Like the higher the dimensionality of the space goes, the vastly more likely it is.
Matt, Moshe is trying to communicate, but there's an echo.
There's
Moshe, you
something-
have an echo.
There's
We
something
can't
happening
understand
to the sound. Yeah,
Let me
pretty
get
bad.
Here, Moshe, I'm gonna mute you for a second. Does that help it? Okay.
Yeah.
So
You're saying that because the electron say passes through one cloud, and there's so many degrees of freedom there, that it becomes a very different history than.
yeah, like that vector is associated with going up and interacting with the red gas, and the vector associated with like going down and interacting with the blue gas are almost certain to be orthogonal. And therefore they can be added without any interference.
And the idea being that you've sort of you've increased the number of dimensions from 2 to some huge number by all the states of the particles that are interacting with it. And then you get this argument of high dimensionality means approximately orthogonal.
Yeah. So like in the case of the spin, you can think about it like this. Like suppose we start in an X plus state. We could represent, you know, this thing as a density matrix like this. It's a little guy with all 1/2s, okay? And, you know, the way a density matrix works is that, you know, along the diagonal are like the probabilities for it to be up and down. But note that there's these cross terms, and that's in the case of spin, like the quantum coherence. And what this means is it's not just like, oh, it could be up half the time or down half the time. It means specifically it's pointed in the X plus direction. After all, it could be pointing in the X minus direction. And then you'd get the same probabilities, but different cross terms. The idea is that if we add this gas to either path, and we look at what happens to the density matrix once this decoherence is set in, these off-diagonal terms vanish. And we get a mixed state, which is compatible, you know, with many pure states. In other words, oh, it could be pointed in the X direction, could be pointed in the X minus direction. It could even be pointed in the Y plus direction, the Y minus direction. All those things give you the same probabilities for Z plus and Z minus. So this can be interpreted as a classical statistical mixture, as if it was either up or either down, each with a certain probability. You just don't know which one.
And that's the point. That's a classical experiment.
So,
But only because, so you've sort of, you're motivating a picture of decoherence, right? That interacting with an environment causes this orthogonality to emerge from there being so many degrees of freedom.
exactly. So this is why, you know, we don't see interference effects generally in real life. I mean, this is why quantum coherence is fragile, and why these quantum experiments could only be done once we've been able to like sufficiently isolate things from the rest of the world.
But then it's interesting of like, is there any kind of microscopic picture you can flesh out about the interactions with these many particles? You know, they're like at what point it's a continuous process, I guess, the decoherence.
Yeah, it's completely unitary. It's just there's some unitary evolution that's basically entangling the, you know, the spin with these guys up here, and it's entangling these guys down here. There's no projection at all.
Right. So you would want to have some sort of like long range interaction, not just like a grid, so that it kind of bounces off one of the many, and you don't know which one it bounced off, but it's kind of like has like a Coulomb interaction with all of them. So it's kind of, you want it to quickly feel all these degrees of freedom. Interact.
So you could imagine, so like when people study decoherence, it's sort of like, all right, well, given some, you know, specific setup, you know, what can we imagine? Like, what are the, you know, what happens basically? in the following sense, like we start off with a density matrix like this, and then our spin, you know, gets entangled with these guys. And so when we recombine the beams, instead over here, instead of getting the coherent density matrix, we get this mixed state. I
don't quite understand
but crucially, depending on the dynamics,
how the change takes place on the basis of the diagonal relationship between the quantities. How does, can you explain that?
So, you know, when people study decoherence, the idea is like, they're gonna study like, all right, you have this system and, you know, it's coupling to the environment, has certain symmetries, and therefore, like in the limit, when this environment is very large, we can say, oh, you know, the cross terms are gonna vanish, and we're gonna end up in this particular mixed state. And, you know, in order to, you know, determine that, you're gonna have to like analyze, you know, a specific instance or a specific class of instances and so forth. But the point I wanna make is this: given some like arbitrary dynamics or whatever, you know, this mixed state could be anything, right? Like it doesn't have to be a half and a half. You know, it could be this probability and that probability. It could be like, you know, 1/3 and 2/3, right? There's no reason that the probabilities along the diagonal are the same for this coherent one and for this mixed one. And I bring that up because in the case where it does happen that way, where the interaction with the environment leads to a vanishing of the off-diagonal terms, and the probabilities are the same probabilities that you start off with, we could define that as a measuring device. In other words, what a measuring device is like a large environment, like a large apparatus that we use to measure tiny particles. And they have the property that like experimentalists have learned that when, you know, you send a little coherent state guy and you have it interact with this measuring device, the thing ends up in a mixed state with the same probabilities as the pure state that originally went in. So that's how we can define what a measurement apparatus is. It's something that, you know, triggers decoherence in such a way that, you know, the probabilities are preserved. So then I want to, oh wait, I can't, are you guys there? I suddenly feel like oh, okay, sorry. Someone's video is frozen. Okay.
Can I say something? In classical physics, a measuring device has a very negligible effect on the system configuration. That's why it's a valid measuring device. In a quantum experiment, our measuring devices are orders of magnitude larger than the system that we're measuring. So of course, the measuring device is changing the configuration of the system. It's not about decoherence or coherence or probabilities. You're changing the configuration. That's why you're getting the original results. Because if you work it out according to Bohm, then you lose the interference pattern because you have a different configuration.
Okay, how about I'll say this. Like, the reason I don't want to treat Bohmian mechanics as given is because I believe that space and time emerge from other things. I don't know if it's the loop quantum gravity people are right, and, you know, space is really the spin network or whatever. In other words, in order to do Bohmian mechanics, I have to assume that space and time already exist. And I'm not willing to do that.
Well, then let's forget about
space and time from things that aren't necessarily spatiotemporal. So like, looking down the line, I'm not gonna like tie any of my interpretations of quantum mechanics to anything that assumes that like I can even assign position states to things.
Let's forget about Bohm. I'm sorry I brought it up again. But the point is, when you introduce a macroscopic device to measure a microscopic system, of course it's going to dramatically change the system configuration. So why should we be surprised that the interference pattern is affected?
Take a case of say like of a photon. Maybe it's like a little cleaner than the Stern-Gerlach is to consider a photon that is incident on a a piece of material that has a probability of transmission and reflection, and similar to like that's the non-uniform magnetic field equivalent in the Stern-Gerlach. I mean, there's nothing like violent happening in the Stern-Gerlach experiment. You can imagine like the particle. Okay, stick to the Stern-Gerlach. Oh, sorry. So it goes through the non-uniform magnetic field. There's no real violent perturbation. You can make the field very weak if you want, as long as it's non-uniform. And then you let you put some fluorescent plate at some point along the way, and the electron will just crash into it, and it'll glow green there. Yeah, that's very disruptive at that point because it's crashed because you interfered with the path. But I don't see the concept, all the kind of behaviors being explained by some sort of interference by an apparatus there, like explaining the concentration of the electrons into two spots as being explained by, imposing a very destructive apparatus.
Well, I was thinking more in terms of the classic diffraction pattern, but even the kind of experiment you're talking about, again, can be explained classically, has been explained classically. I don't understand the introduction of quantum physics in this experiment, except as an unnecessary.
Well, I'm not familiar with the. What's the classical version of it?
Well, all this, I mean, if you're talking about photons, all this stuff can be explained classically. I don't understand why we're talking, again, let's say you're talking about an experiment where you're using polarizers. So you pass it through one polarizer, and of course, the ones that are polarized in the right direction are going to get through. And then, of course, if you pass it through another polarizer, only the ones that had the original polarization are going to get through again.
What makes it a quantum thing is that, you can send like a single photon at a time through the thing, or in the double slit experiment, a single particle. And so what makes it quantum is that a single thing has to be regarded as taking two simultaneous paths.
No, but when you send,
what it is.
But the polarizers is a good. I think the polarizers is actually a cleaner case than the double slit, maybe.
When you send a single particle, through the double slit, it lands at a particular point on the final screen. You can decide which slit it went through. It doesn't go through both slits. It goes through one slit or another.
Let's stick to the polarizer. I think that's cleaner.
I want to make a point here, which is, before we try to settle some of those interpretive questions, the point I want to make with like where I'm going with like these next couple sections is simply to analyze what measurement means in the orthodox interpretation of quantum mechanics. So like before we like talk about like whether it ultimately makes sense or not, let us just analyze what the mathematics is telling us about how it works.
Right. It's like
then we can figure out
study some religious belief system that we don't believe ourselves. Yeah. We can still like explore all the consequences of those axioms.
But we have to realize
about what it is that we're talking about here.
We have to realize that measurement in the classical sense is a device that does not appreciably upset the system configuration. Measurement of a quantum system dramatically, by orders of magnitude, changes the physical configuration.
Basically, there isn't really.
We're talking about two different things.
One of the classic things that we talk about when we talk about measurement is the so-called measurement problem. In other words, why do we perceive one outcome over another. And okay, yeah, Bohemian mechanics, something. But let's look at like what the math is saying, okay?
Stop laughing, Victor. This is serious. And stop torturing that bird. We're going to report you.
So, like, the point I want to make is, people often wonder about, okay, you have this sort of chain of causation. Like there's a spin, it gets entangled with position, which gets entangled with this, which gets entangled with this. And then, you look at the result of the measurement or something. And a question arises, like where, if one outcome appears over another one, when does that happen? Does it happen when you make your final measurement? Did it happen way back when the spin went through the Stern-Gerlach? Did it happen when, there were these two gases, and so it collapsed, when, one half went through this gas, the other half went through that gas, right? Like we could regard the collapse as happening here because, if we recombine the beams, we'd lose the coherence, and it looks like a classical mixture of taking the up path or the down path.
Yeah, but rather than talking about superposition, I mean, it's passing through a device of a certain length, right? The silver atom. Mm-hmm. And so at a certain point, it's no longer sufficiently under the influence of the magnetic field once it passes through the Stern-Gerlach device, that the final state of up or down of that particle is going to be affected, at the end point of the magnetic field, and it's going to distribute up or it's going to distribute down. So you don't even have to talk necessarily, and I'm not trying to be Bohmian here, you don't have to talk necessarily about superposition at all. The final state up or down as it reaches the end point of the magnetic field is going to.
Why would that be the case? I mean, as it goes through the magnetic field, its spin gets entangled with its position, and then it's in a superposition of being up and going up, down and going down, and then once it's out of the range of the magnetic field, it just stays in that position unless
because Matt, it had a propensity. It had a propensity to be up or down. Forget about superposition. It had a propensity to be up or down, and that's why it retains its original propensity.
Has the Stern-Gerlach experiment been done recently in such a way that they can actually measure at the end how many of the silver atoms are shown with spin up and how many are shown spin down? Is it exactly a 50-50 distribution? What is
yes? It's 50-50.
I don't think there's any doubt about
50-50 because randomly that's how they're distributed.
You combine the beams and so forth.
Yeah, light is cleaner. People use light usually.
Yeah. Like you can't just explain away the superposition thing. One point I want to make though is this. Well, people often say that decoherence solves the measurement problem because, for example, if this guy goes through this gas or this gas, the coherence disappears, and if we recombine the beams, we get this statistical mixture. So it's like, so because of decoherence, it's one or the other. But that's not, and even the experts will tell you, like, that is not strictly true. In other words, until I measure this guy in some way, this mixed state is still potentially provisional. Why do I say that? Well, what if instead of taking this guy and sending him through a Stern-Gerlach apparatus and measuring its X and doing the experiment a bunch of times, X, Y, Z, and then recovering its state, what if instead I reverse time? In other words, I take this gas and I take this gas and I have it interact again with this guy in such a way that completely reverses the dynamics that it originally went through. If you just undo the time evolution, so to speak, then you'll restore the quantum coherence. In other words, the reason decoherence is relevant is because almost certainly you won't be able to do that. To the extent that this is like a shit ton of particles and this is a shit ton of particles, you don't have control over them. You have no way of, in a coherent and controlled way, taking this particle, having it like interact again with these ways in precisely the opposite way to like undo the interaction. But if you could, then you would have to say, oh no, you know, maybe there was decoherence here, and then for a second there, this was in a mixed state or like whatever. And so the filter happened over here, but then some other shit happened, right? These guys interact and then all that's undone, and then we restore the original coherence.
Is the shit ton of particles, is that a technical term for decoherence?
That's a technical term.
It is now.
This theory, this
like
is
a
the same
spin echo,
theory,
right?
the same theory. There are no women here, are there? This is the same theory. If my grandfather had teats, he would have been my grandmother. You can't go back in time. This violates causality.
It absolutely does not. Quantum mechanics is like time reversible. I mean, pretty much all the laws of physics are. Like if
there are systems that evolve where basically the wave function evolves into an eigenstate, you know, a clean one, and then continues to evolve and goes back into superposition over time.
It's just you have a unitary.
And that's actually utilized in MRI. But, yeah.
Sure. Like you have a unitary evolution, and you can just take its adjoint, you know, the conjugate transpose, and that'll give you the time reversed.
Mathematically, not physically.
Well, in practice, you're absolutely right, Michael. Like it's like you can't just reverse the measurement, right? It's like if, like imagine like, okay, I measure the position of a particle, like the thing hits a photographic plate and it develops or whatever. In order to reverse time, what would I have to do? I'd have to like undo all the interaction like among all the things on the photographic plate and like da-da-da-da-da. Never gonna happen.
When physicists talk about reversing time, what they mean is unitarity. They're talking about causality. This is the point, that unitarity means there's a causality and you can't go backwards. Yeah, mathematically you can go backwards, but not
you can
physically
undo it, is what I'm saying. There's just a simple, you just literally just take the conjugate transpose of your propagator, and
you're talking math, you're not talking physics.
But in principle, the projection, when you do a projective measurement, that should be irreversible. But I say, oh, you just do a projective measurement, I'm kind of like hiding a lot of microscopic details in that phrase.
Yeah, exactly.
And you're kind of trying to zoom into them right now.
So what we're trying to do now, see, can we explain the appearance of a definite outcome, in other words, a projective measurement, solely through the unitary dynamics? And we thought for a second we could because of decoherence. If there's these gases here, then we lose the ability to recohere the beams and recover the original state of the particle, and it seems to have collapsed to one or the other. But what I'm saying is that that's still provisional, because you could continue your experiment and reverse time and get the coherence back. What I'm saying is that in general, that's going to be impossible. You're never going to be able to, put the egg that's broken back together. But in the micro world, it happens all the time because it's not that hard. In other words, if I use my measuring device and then as I say, makes a dot on the photographic plate, to reverse time, I have to undo the entire fucking process of making a picture. Not gonna happen. But if it's 4 particles just interacting, then it's perfectly possible that the unitary that reverses time can be undone. If you're just considering several quantum particles, it's not at all trivial. I mean, it's not at all.
Matt, you're not. Matt,
the reverse transformation is going to happen.
Matt, you're not undoing a process. What you're doing is predicting where the current state came from because of unitarity. You're not undoing a process. You could never reverse time. You can reverse time mathematically, but physically, that's not what you're doing. You're just showing that the current state was caused by the previous state. And yeah, for one or two particles, you can very easily figure out where they came from.
Like,
if you break an egg, it's too difficult to figure out where it came from.
So if you just have a couple particles and, you know, they evolve with some unitary, it's not difficult to engineer a unitary that does the opposite thing. Like, you do it all the time when you're working.
Yeah, you can figure out where it came from, but you can't go back in time.
Well,
That's the grandfather paradox. I can't go back in time.
Well, I'm not saying, okay, look, I mean,
it's not actually time travel.
Going back in
restoring
time,
it to the original state.
Like, kind of
it's like you having some number of unitary operations on the wave function. You're adding more unitary steps.
But this is the point. Unitarity proves causality. Unitarity means causality.
All
to go back in time to
like when you talk about going back,
is impossible.
Reversing it, you're comparing it.
Mike,
you're still comparing it at two different points in time.
Take it easy.
Yeah, I'm not talking about going back in time. I'm saying that if there's quantum dynamics, then the reverse of those quantum dynamics are perfectly good quantum dynamics. If I have a unitary matrix, take the conjugate transpose, and I multiply them together, it's just the identity matrix. Like, that's the whole point of unitary matrices. Unitary matrix times its conjugate transpose is the identity. In other words, it's like doing nothing. So if we include decoherence in the picture, it seems like we could say this filter or this collapse or this projective measurement happens, you know, when it goes through the gas or something, because we get this mixed state. But you could really say that that's just a limitation of our ability to control the system. If we did have complete control of the system, imagine the whole experiment was, you know, confined to taking place in a big sphere, and like nothing could escape the sphere, and we had like all these fancy shit, we could like control everything. Then we could even reverse a macroscopic measurement, and in the case of, you know, just a few particles just bouncing around at the micro level, that might happen all the time. So the point is that even that mixed state due to decoherence is sort of provisional. We can't rule out in principle some clever phenomenon that precisely implements the reverse unitary evolution that recovers the coherence. And so, you know, operationally, it looks like, and some people have taken this conclusion to its logical extent, as we will see in the next moment, it's only by actually measuring the particle ourselves that we can say a definite outcome occurred. In other words, until you've made your last measurement, there's still a possibility that something else could happen. In other words, oh, you know, start the spin here, decoherence, get a mixed state, and then I measure it. Okay, sure, it collapsed when it went through the gas. But if the ending of my story is different, like, oh, instead of deciding to, recohere the beams, instead I, reverse the gas interaction, boom, the coherence comes back, and then I make my measurement. I get something different. In other words, to make sense of quantum mechanics and the kinds of stories that quantum mechanics allows us to tell about the world, here's the thing that separates it from classical thinking. You have to fix the beginning and the end of your experiment. You can't leave it open. To leave it open leaves the possibility that there's some other thing that could happen, that, oh, maybe you decide not to recohere the beams and measure position, or this or that or that. Until the beginning is fixed and the end is fixed, you can't say definitely what is the history that the state took from the beginning until the end.
This is what I do. Before I begin my experiment, I sign a contract with my photons. They know they're in this omniscient state, and they know what their condition is going to be at the beginning and at the end. That's how I do it.
Well,
I think the other day I was like meditating on the similarity between like the human concept of a contract and the idea of like entanglement and stuff.
The concept of what? The human concept of what?
Of a contract, like a legal contract.
A contract, okay.
you know. So
I wonder if you know, like, what is the, certainly by introducing a huge number of particles to induce the decoherence, it kind of reminds me of the notion of like a, you know, if you draw a marble out of a bag of a bunch of different colored marbles, and then you want to do like an identical draw, you throw the first marble back in, and then you shake the bag up, and shaking the bag up is like an imperfect way of creating another random set, but it's imperfect. It's kind of, you're pretending a little bit. So like, just like by adding it, like you're making it so that you're not going to realistically be able to know, you know, what you did to the bag, but you did. Anyway, it's not random. But anyway, but like by adding a whole bunch of complexity, you're sort of making it just like an intractable situation to try to tease out. I wonder, like, what is the simplest, or what kinds of simple cases might exist where you could say, like, you only actually need, you know, 5 things, and then you end up getting what we would all agree is a measurement outcome, you know, and to be able to like reduce the amount of excess complexity.
yeah,
But I wonder, like, if we had like a photon go through a beam splitter, and then like my eye is lined up with one of the paths, like my actual retina, you know, which, and my understanding is that retinas are sensitive to a single photons, that like me seeing it, you can get more direct than that. Like, I saw a flash of light, you know, I didn't have to go to a computer first, and then I looked at the computer screen or whatever.
Yeah. So, right, so that brings up the interesting point, right? So in that case, you are acting as the measuring device.
Yeah.
Now, some people would say, and we'll like talk about this view coming up, that like, oh, it's your consciousness or something that collapses, the wave function or whatever. You don't have to go that far, okay? Because you yourself are like a huge macroscopic being introducing decoherence. Like, in other words, once you've, you know, measured once you've looked at the, you know, the photon enters your eye, you know, imagine all of the complicated shit that would have to go on to make you forget in every sense that that ever happened. It's going to be very unlikely for you to be able to restore the quantum coherence and reverse time, because that would involve like reversing the time evolution of your body. In other words, just like you know, a normal way of measuring precision or whatever, you're a big thing too. And so the idea is that like big things stabilize facts.
Right. Yeah, sure. I mean, like, my retina has a whole bunch of molecules in it and stuff. But I guess it's kind of like that's the whole thing with quantum mechanics. You never fully escape, you know, these fundamental philosophical problems. Like, it's like any situation, I'm going to say, yeah, I confirm that I agree that the outcome of the measurement was whatever. It's because like I saw something. So okay, those were photons coming off the computer screen into my eye. Like, okay, but that's like well after the fact of the actual measurement. Like the fact that I had like my macroscopic retina involving itself, you know, is sort of not really relevant to the actual measurement itself. But like, you know, well then I can't get more closer than just putting my eye directly in the, like, there's always going to be a whole bunch of macroscopic stuff in between you seeing what happened and the quantum event.
Yeah.
Is there any situation where you can remove any, even in principle, like a situation where like there are no obviously
well, so dude,
large objects involved?
If there was, then there would be none of this confusion about, you know, what's the relationship between consciousness and quantum mechanics. Like, in other words, you know, there's this huge gap between, you know, neuroscience and biology and stuff and the quantum physics. You know, if we could do those kinds of experiments and somehow in ever more unmediated ways interact ourselves with quantum systems, then maybe we could answer some of these profound questions. But I would argue, like, until we have that technology, we're just still going to be arguing about it. We're dealing with a fundamental technological limitation. There's not enough empirical data.
Michael Fischbein was saying that that the retina is sensitive to a single photon. The same rhodopsin molecule that's in the retina is inside of one-celled light forms. So as far as this relationship, you know, over the evolution of the cosmos between the macroscopic measurement device, the human being, and and the particles, right? As the very first life forms arise, the same capability of sensitivity to a single photon existed.
I love that.
That's not entirely true, Victor. Different species have different interpretations of electromagnetic waves. But the point is this. The point I wanted to make is that the universe exists and goes on irrespective of our consciousness. The universe existed before we did, before any life on Earth existed.
On the decisions that
I don't think consciousness being essential is a popular attitude.
Yeah.
There are some people who think that consciousness is the collapse of the wave function. I mean, there's a guy in Arizona whose entire
there's a lot
career,
of people. True. So where does that come from, by the way?
It comes from, he had a bad dream.
Yeah. So it comes, this is the crazy thing, right? That view comes from the foundational text of quantum mechanics. In other words, the mathematical foundations of quantum mechanics by John von Neumann, published in like 1932.
Again, I have to say, mathematics is not physics. You can't invent the mathematics and impose it on the real universe.
He defines something called, so again, now I'm going to talk about this. Again, I don't know what is the relationship between like my experience, my inner experience as such, and the world as described by quantum mechanics. I think it's a question which we don't have enough data to answer yet. But we can talk about like why different people have thought different things about these issues. And one of that paper that I suggest you guys read, I like because it sort of treats many of these different possibilities and shows that they're all like logically coherent, but it's a question of relating it in a sense to experiment. So when one makes a measurement, because of the linearity of quantum evolution, one can regard the so-called collapse as having taken place arbitrarily along the chain of causation leading from the system to you. And because of this mathematical feature, von Neumann makes this claim at the end of his book that quantum mechanics implements what he calls the principle of psychophysical parallelism. Now, this term, arose out of like 19th century science.
Yeah.
And was like a relatively popular viewpoint. It's a sort of version, a kind of nuanced version of Cartesian dualism. And, he defines it, and then he provides a little mathematical theorem that quantum physics respects it. Now, you can interpret that how you like, but there's a mathematical proof involved, okay? And of course, all mathematical proofs come with assumptions.
And the correct interpretation is that it belongs on the garbage heap of scientific history, along with phrenology, which was mathematical, and eugenics, which was mathematical.
Michael, this is the thing. This idea, this like fantasy that the world goes on completely independently of us is from another perspective, you often frame it as like something, arrogance versus humility, how arrogant it would be to think that the world depends on like what we measure about it. The most humble position is to realize that the world goes on independently of us. But you can flip that around. What kind of arrogance leads you to think that the world doesn't depend on you? Like
what a measurement
is, hold yourself apart from the world. Like we're all in this world together, and the decisions we make all affect each other. In other words, it's a complete fantasy that we could ever hold ourselves at a distance from things. And to imagine that we are not an equal participant in this world as any other thing.
Matt,
so
measurement.
You can't use the argument from arrogance versus humility because it goes both ways.
Measurement is given a special place in the Copenhagen interpretation. Measurement is nothing more than another physical interaction. That's all it is. It's an interaction, and interactions have gone on in the universe long before life on Earth ever existed.
The fundamental mystery that's
not a mystery
happening here. Okay, so
it's only a mystery to Niels Bohr, who was married to Copenhagen. Copenhagen makes it a mystery, but it has been explained. And
It
yet,
has not. It is absolutely
What,
not.
what,
Bohm explains it, and Bohm makes everything
Michael, if I
deterministic.
might ask you, what
Completely
do you
wrong.
find interesting
This
about the
is the
subject? Because
entire
it seems to
point.
have no mystery for you.
No, because obviously quantum physics is different from classical physics. But to say that it's a black box mystery,
It's
no,
not.
it has been explained since Copenhagen, was invented. Bohmian mechanics and its successors explain a deterministic quantum physics. And then all this stuff about superpositions and probabilities are all nonsense. It's just that this is what they still teach. And it's a
Well, I don't
political
even know
decision.
that Bohm would be as enthusiastic about it as
I'm
you're.
sorry?
I don't think Bohm necessarily would share your enthusiasm. Under your
Bohm is
advice,
deterministic. And by the
I
way,
did go into the
quantum field theory is not a successor to Copenhagen. Quantum field theory is a completely different theory.
Yeah, it's
And,
not really.
and it is deterministic, by the way.
well, there's one alternative thing that we have not
just
mentioned, which is
bullshit.
the sum of all histories.
Wait, what's bullshit?
Quantum field theory is a natural, seamless generalization.
Well, you can say
Of
anything
quantum.
is a natural successor to
And it
anything.
doesn't
that
change
Yeah, but you'll be wrong a
anything
lot of
about
times.
the measurement issue.
But it's a
the same
different
issue.
theory.
It's the same problem. Okay.
Depends
The
on
thing
how
is,
you
like,
interpret it.
I don't want to, again, my point in doing this is not so much to push a particular view like, oh, the measurement problem's been solved and it's this, or the measurement problem's been solved and it's that. What I aim to do is show what the stakes are. In other words, if you look at the formalism of quantum mechanics, just like in special relativity, it's like there's things that everyone agrees on, right? And then there's things that people disagree on, right? Different observers could be like, oh, this event happens before this one or after that one. So there's a kind of symmetry. The same thing applies in the issue of quantum measurement. In other words, there are many different things you can imagine, like the collapse happened here or here or here or here, that don't affect the final outcome of the experiment in any way. In other words, the mathematics of projective measurement, there's a certain symmetry to it. And this is why, it's bullshit when people talk about the inconsistency of collapse with, say, special relativity. Because they say, oh, well, if the collapse happened here, but if this person had a different clock measurement, then da-da-da-da. The thing about collapse is, in general, it does not matter when it happens. It can actually be regarded symmetrically as happening at any point along the chain of causation from the beginning of the experiment to the end of the experiment, once you've fixed that particular experiment.
So Matt, let me ask you, how do you...
of the measurement problem, in a sense, has to deal with that fact. You see what I mean? It's that's part of the mathematical nature, the structure of what this thing is.
So Matt, I have
to interpret it, we have to understand it.
I have a question. You believe in unitarity, yes? Collapse of the wave function violates unitarity. It is a mathematical discontinuity that violates unitarity. How do we explain that?
Well, just for the record, I did see in Bohm's paper, I think it's part 2, he talks about, when you do your measurement, yeah, you're disturbing things, but also the quantum potential goes into an eigenstate of the apparatus. He talks about the quantum potential basically behaving discontinuously.
Right. And
he doesn't use that word because that would be too damaging.
Quantum potential is a non-local phenomenon. It happens instantaneously.
Aside from that huge issue of the non-locality, but that the time evolution of it is also not continuous.
No, that's not true.
He said that you
that's
make a measurement,
true.
it does not smoothly go.
If Bohm stated that, then he corrected himself, or it has been corrected. It is a non-local.
Yeah.
It is a non-local.
That's why I asked that if there's any kind of very recent insights that have
it's a non-local phenomenon, but it's
unitary.
Problems. It's unitary, and wave function collapse is a non-unitary phenomenon. It is it's a mathematical discontinuity. So how can you have wave function collapse and unitarity? It's a contradiction.
Yeah.
That's why it's so interesting.
Here's what I would say as someone who is about as unwise as anyone could be. I would preach the wisdom of agnosticism on all the different schools of interpretation of quantum mechanics. Obviously, Copenhagen is dominant or utterly dominant. Obviously, Bohmian mechanics is still somewhat peripheral, but it may be rising somewhat.
It's not peripheral, Victor.
There are
I
other schools of interpretation as well.
No, Victor.
That's right. Let me just finish. So the best way is to be a perspectivist. The best way is to entertain all of the theories. When you're doing your actual quantum mechanics for applied quantum mechanics, well, shut up and calculate. When you're not calculating, then be a philosopher, inquire, remain open to all the possibilities, turn them about in your mind, and try to, as Matt Weiss, who should be trying to go to MIT, Stanford, Princeton, Harvard for graduate physics, invent your own school.
No, Victor, you're missing the point.
And also remain maximally agnostic.
Victor, you are missing the point. The reason Bohm is not taught, the reason Bohm was ostracized is because—
You're going to bring the politics in.
Excuse me, let me finish. It's because he was accused of being a communist, and he went into self-exile. And by the way, physics, like almost everything else, has become political. You realize that string theory, in which there is no empirical basis, dominates Stanford University, Columbia University. This is all political.
Well, but Michael, if you read if you read that Xavier University thing, you can see that, in 1962 or whatever, like all these guys, Wigner, Dirac and stuff, they speak very kindly of Bohm, and they talk about his theory. You have to remember, a lot of these fucking physicists
Bohm is not inconsistent.
I mean, Einstein
is not inconsistent with Copenhagen. Bohm is not inconsistent with Copenhagen. But why would you choose a probabilistic theory when you have a deterministic theory? And Bohm is completely consistent with Copenhagen.
In the case of non-relativistic, the simplest, trivial kind of quantum mechanics you can imagine.
Copenhagen is not relativistic too. Copenhagen is also not, and that is why I said QFT.
If I may ask a question,
I said QFT is not Copenhagen. QFT is a completely different theory. It's about second quantization. It is about excitation of real field.
Michael, can I ask you something?
That is completely different from Copenhagen.
Okay. I'm interested in knowing more about what you think about Bohm that makes it so compelling. So I would ask you to point out any kind of references that correct lingering fundamental issues.
Google it. Read the Wikipedia entry. That's a starting point. That's a starting point. And then you can go on from there. It'll direct you to papers.
Well, I'm reporting back from that project, and I'm saying that I don't want to go digging anymore because it's so time consuming. If you know of where certain issues that are longstanding have been resolved, to please point them out, because I don't want to spend the time to go.
No. But you didn't hear what I said. I said that Bohm is completely consistent with Copenhagen, but why? But it's deterministic. Why would you choose a probabilistic theory, a theory that makes probabilistic?
Non-local is in no ways obviously better than not deterministic.
Again, I meant
non-local has nothing to do with deterministic.
You choose the indeterministic theory.
Non-local can be deterministic. Non-local is not necessarily.
No, I'm saying it. Why is that any better?
Matthew's trying to respond, Michael.
Because because you can predict trajectories of particles. Copenhagen does not.
I would say that since Bohm is, I can't find where Bohm says where he clarifies these points. Because this
is one of the reasons
books,
Bohm is
I have all of this stuff.
Bohm does not give you
as good as the alternative.
Bohm doesn't give you.
And everyone wants to work in direct notation anyway.
Bohm does not give you different predictions. Bohm is completely consistent with Copenhagen, as it must be, or else it would be wrong. But it gives you deterministic predictions for individual particles. It gives you trajectories, actual trajectories, so that a particle
But
doesn't
if
go
it's
through both
equivalent, then why can't
slits.
we just
A
stick
particle
with
doesn't go through
our
both
preferred
slits in a
orthodox?
double-slit
Michael,
experiment. It goes through one or another.
Michael, the analogy I make is like when I'm running a simulation of quantum mechanics on my classical computer, right? It's like I have to simulate the random outcomes of measurement using a pseudo random number generator, and so they're not really random. And similarly, because the entire state of the simulation, you know, is just like expressed, you know, in my like computer memory. I can like, you know, there's really no difference between here and there. Like there's really no notion of locality and so forth in terms of like its representation in the computer memory.
But
I can get exactly the
random.
same predictions as quantum physics. And it's a completely classical thing. In other words, it's not enough to say that you get the same predictions from a deterministic theory. That does not imply that the world's actually like that. Like, it may be true, but that's not enough to prove what you're saying it's proven.
Do you think that nature works on probabilities? Nature works according to rules, because we can't explain those rules using anything other than math is our deficiency.
I don't
Nature
understand
knows exactly what it's going to do.
I don't understand why it's implausible that the universe works by rules and the rules govern the evolution of probabilities.
No, that's a contradiction.
That crazy?
That's a contradiction.
Probabilistic.
You have rules or you don't have rules.
Why do the rules look? If to me,
because Copenhagen is the wrong interpretation.
If we're going to spend so much time
a universe that's deterministic.
Air to
me,
I'll say if you're going to spend so much time on this, I feel like I don't learn anything more about Bohmian mechanics.
This is too much.
And we spend so much time on it. I'll say, like with Michael, if you want to take the floor in defense of Bohmian mechanics, I would appreciate
okay, well, actually,
educating me more about things that would help me to appreciate it as well as you do, but not just sort of insisting that we don't talk about things that Bohm does not. I
did give a presentation at the New York Quantum Meetup.
But because I missed that, the rest of my existence.
This information is available. You can find it easily by Googling it.
Then I think you might have misinterpreted some of it, because what is available easily is not sufficient. Specifically, I will just ask that there's a direct challenge from the Cohen-Specker theorem, which I did not see any Bohm response to that. There's a particular thing that is in direct contradiction with the Bohmian mechanics.
Well, Copenhagen is a direct contradiction to actual physics too.
No, but I'm talking about something specific.
Copenhagen is non-relativistic. It doesn't predict particle creation.
I think that
Copenhagen is just a theory.
And I'm in favor of what I don't want this to always turn into almost. I'd like to hear what Matt had in mind to present.
We should go on, but we should also realize that, again, mathematical theories are not physics necessarily.
Also consider
it's a weak attempt by us to explain what we see.
Look, what separates
your message has been heard, I think.
Yeah, it's true. What separates physics from philosophy is that it's the art of making mathematical models of the world. There is no physics without mathematical models.
So string theory is math. Does string theory explain anything? It explains nothing that we can measure.
That's something that can be answered by comparison with experiment. But what I'm saying is that you can't have physics without math. It's just inconceivable.
Well, because of our limitation, because of the limitation of our brains.
The process of modeling, like what we mean by having a physical theory.
You think that nature uses math? You think that nature has any conception of math?
I don't think
nature works according to rules.
Seriously is claiming that.
The math is our weak attempt to approximate what we see in nature.
You confuse your models.
And usually we're not that accurate, by the way.
Okay, so let's move on a little bit. Like, I just wanted to.
I apologize.
No, it's okay.
I would say, personally, for me, if we can't talk about some of the
argument of quantum mechanics, determinism versus randomness, and so it's entirely appropriate that debate, which was initiated between Einstein and Bohr all those years ago, continues, you know, with all of his fieriness 100 years later. Like that is entirely appropriate. So, you know, you don't have to apologize for anything, Michael.
Yeah, I find this stuff fascinating. This is what is so interesting about quantum. But I would appreciate it if when we do get into it, we can sort of be maybe challenging, like Einstein and Bohr. You know, they come up with specific examples, counterexamples. You know, not just sort of insist that this has all been resolved already and kind of like make a historical claim. You know?
Yeah, I agree. I think the agnostic position is the most sensible.
Well, Einstein and Bohr completely disagreed with each other.
Here's the way I framed it.
But they were both wrong, by the way.
To take it outside of Einstein and Bohr, and to take it outside of Rome versus Copenhagen. Okay.
Mm-hmm.
The probabilistics that are used in quantum mechanics apply to every single scale in nature. There's no distinction between the quantum realm and classical realm in this sense. The probabilistics are there for Brownian motion, for the climate system, for the three-body problem in space, and for cosmology. So this supposed distinction between the Copenhagen interpretation and physics as a whole simply doesn't exist. Okay, every single branch of physics at every level is using computer models that are probabilistic. So the issue is not one of indeterminacy. The issue is of our inability to determine, a lack of determination on the part of human beings using either our senses or using instruments of what is occurring in nature in relationship to what can only be logically a deterministic universe. I think that there is something actually fundamentally anti-science in the notion that something lacks determinism at any point. That is to make the cosmos into something that is random at any point is to deny that there's any possibility for coherence, any possibility for rule making, any possibility for a mathematical model that's going to expose accurately the nature of any phenomena on any scale. What we have is a universe that is deterministic, and we cannot determine it at any level with perfect accuracy. What we have is in the age of the sciences of complexity, of chaos theory, of ordered disorder and disordered order, of the complexity existing at once again at every scale, from the cell to the tissue to the organ to the bodily system, like the nervous system. It is inextricable complexity. We can't determine it, yet it's deterministic.
And you know what the problem is? The real problem, and we keep confusing randomness and statistics. We don't know. The reason we can't make good predictions is because we don't know the initial conditions.
Right.
We only know it statistically. Now, Matthew and other people are calling this randomness. No, there is an actual statistical distribution over many particles. It's not random, but for a single particle, it is completely deterministic, but we don't know how to measure those initial conditions. That's the crux of the problem.
You can find the error
disproportionate
within
amount of time
language.
to this.
You can find the error within language.
This is a minority opinion in the physics community.
Yeah, let's
you
move
can find the error within language. Look at the word accident, which leads to the notion of randomness. There is no such thing as an accident. Two cars are approaching one another. Each has a trajectory. A person hits this bump in the road or has to turn because of a bicycle that appears between two cars on the side. Actions are taken, forces are applied. The cars don't hit one another by accident. They hit one another out of necessity. The notion of accident and randomness are errors that are in the language, which then become philosophical notions applied to physics. This is not science. This is a grave philosophical error.
I see your point, and I'm totally open to the possibility I'll say one thing, and then I want to move on from this, which is just, I'm not sure if determinism and science as such are so intimately intertwined, in the sense that, I mean, just to me personally, perhaps it's only at an emotional level, a universe which is governed by completely deterministic rules seems to me totally pointless, because there's no drama. You have some axioms and you have some theorems, and they're all necessary consequences. There's no need for time or change or consequences. Only a universe which is not completely deterministic is at all interesting and has a right to exist. Like, why would God create a world if you have to do everything that happened?
The right to, and this is our value system. This is not the value system of the universe. This is your value system.
I freely admit
that. But I will impose your value system on the universe.
Of the deterministic universe, because it seems pointless to me. Like, it's not.
May I just have my last stuff?
I freely admit that. Like, if I were God, I would create an indeterminate.
We should move on, though.
But if I may just sort of like inject a thing that I think is a concrete point to follow up on sometime in the future. I think it's fascinating. The Kohn-Specker theorem, to me, is not something that Bohmian mechanics is going to be able to handle. And it seems to me to be a really clear, concrete problem for those really insisting that everything is straightforward. We just can't see, clearly enough, But so I would recommend that we go into that. I know maybe in some past time you did, but evidently it didn't leave its mark, because if that's wrong, then I want to know why it's wrong. But
Bohm does not explain everything, nor does Copenhagen. That's why we have quantum field theory.
That makes certain parts of what Bohm claimed
Bohm is deficient, as is Copenhagen. They only describe non-relativistic quantum physics. Neither one of them describes particle creation.
Well, if someone could just acknowledge that I've added to the record my request that we treat the Kohn-Specker theorem, because I think it has an essential thing to say on this matter.
I agree.
I think it presents a challenge that is not a trivial thing to be defeated.
I will look into that myself. Maybe I'll be able to write something up. I think that would be. So
let's move on.
Yeah, let's move on. I just think, again, I'm not necessarily in reading this out, like endorsing it, but I think it's really interesting what von Neumann says, like why he says it, because, this is the guy who is basically saying that consciousness or something does play a role, and arguably he was the smartest man alive. I mean, like,
do you know what
until this paragraph?
Do you know what terrified von Neumann? You know what terrified him throughout his whole life? Talk about the smartest man alive. What? You know what terrified him? Death. He could never come to terms with death.
Yeah.
So was he the smartest man alive? I think a lot of us.
He was the most.
Worked for Rand Corporation.
He was a computer machine. He was the computationally most capable person.
And he's a little outdated by today's.
As for me, I am become death, destroyer of worlds.
Wow.
Oh, you're J. Robert Oppenheimer. You look familiar.
So I just wanted to read a little bit of this passage from the book, okay? So von Neumann says this. He's like, it is inherently correct that measurement or the related process of subjective perception is a new entity relative to the physical environment and is not reducible to the latter. Subjective perception leads us into the intellectual inner life of the individual, which is extra observational by its very nature, like logically, since it must be taken for granted by any conceivable observation or experiment. Nevertheless, it is a fundamental requirement of the scientific viewpoint, the so-called principle of psychophysical parallelism, that it must be possible to describe the extra-physical of subjective perception as if it were in the reality of the physical world. In other words, to assign to its parts equivalent physical processes in the objective environment in ordinary space. In other words, all of our observations, like our language, have a subject, verb, object form. And in any experiment, there's always like a reference to both like what is measured and the one doing the measurement. But insofar as we treat, say, ourselves and we attempt to understand ourselves, we of course have recourse to, oh, well, these neurons in the brain did these things, or this happened over here in my body. In other words, even as we say like, oh, I am observing this, I should always be able to take that I and nevertheless view it as being something that is in the physical world. In other words, my brain. Of course,
I am in the world and the world is in me. That's a simple way to frame it philosophically.
Sure. Of course, in this correlating procedure, there arises the frequent necessity of localizing some of these processes at points which lie within the portions of space occupied by our own bodies. But this does not alter the fact of their belonging to the world about us, the objective environment referred to above. So then he gives an example. We wish to measure the temperature. We could, look at the mercury column in the thermometer and say, this is the temperature measured by the thermometer. We can carry the process further, and from the properties of mercury, we can calculate its heating and the resulting length of the mercury column and say, this is the length seen by the observer. We could take the light source into consideration and find the reflection of the light quanta onto the opaque mercury column and the path taken by the reflected light quanta into the eye of the observer, the refraction in the eye lens, the formation of an image on the retina, and then we would say, this is the image registered by the retina of the observer. And were our physiological knowledge greater than it is today, we could go still further, tracing the chemical reactions which produce the impression of this image on the retina, the optic nerve in the brain, and in the end say, these chemical changes of his brain are produced by the observer. But in any case, no matter how far we proceed, from the thermometer scale to the mercury to the retina or into the brain, at some point we must say, and this is perceived by the observer. Because after all, we aren't just comparing two brain states, we're comparing our experience with something out in the world. That is, we're always obliged to divide the world into two parts, the one being the observed system, the other the observer. In the former, we can follow all physical processes, in principle at least, arbitrarily precisely. In the latter, this is meaningless. The boundary between the two is arbitrary, and that's the key point. It's arbitrary to a very large extent. In particular, we saw in the 4 different possibilities considered in the preceding example, that the observer need not be identified with the body of the actual observer. In one instance, we even included the thermometer in it. In another instance, the eyes and the optic nerve were not included. And here's the crucial line, that this boundary can be pushed arbitrarily far into the interior of the body of the actual observer is the content of the principle of psychophysical parallelism. In other words, you can divide up the world between subject and object completely arbitrarily without violating any physics whatsoever. But this doesn't change the fact that in every account, the boundary must be put somewhere if the principle is not to be rendered vacuous. In other words, if we can actually compare things with our experience. Indeed, experience only makes statements of this type. An observer has made a certain subjective observation, and never any like this. A physical quantity has a certain value. Now, quantum mechanics describes events which occur in the observed portions of the world, so long as they do not interact with the observing portion, and it does so by means of unitary evolution. But as soon as such an interaction does occur, in other words, a measurement is made, the theory requires the application of projection. This duality is therefore fundamental to the theory. Danger, however, lies in the fact that the principle of psychophysical parallelism is violated so long as it is not shown that the boundary between the observed system and the observer can be displayed arbitrarily. In other words, it's only inconsistent to have both unitary and evolution and also projection if you don't show that the boundary line, like where you put the projection, is completely arbitrary. So then he sets this up like a mathematical theorem. Suppose you divide the world into 3 parts, 1, 2, and 3. Let 1 be the system actually observed, 2 the measuring instrument, and 3 the actual observer. It is to be shown that the boundary can just as well be drawn between 1 and 2 and 3 as between 1 and 2 and 3. In comparison to the first and second cases, 1 was the system to be observed, 2 the thermometer, and 3 the light plus the observer. In the other case, 1 was the system to be observed plus the thermometer, 2 was the light plus the eye of the observer, and 3 was the observer from the retina on. In another case, 1 was everything up to the retina of the observer, 2 was his retina, optic nerve, and brain, and 3 was his abstract ego. That is, in one case, which one's which? Unitary evolution is to be applied to 1 and collapse to the interaction between 1 and 2 and 3. The opposite for the other case. And then crucially, that thing which sounds crazy, right? The abstract ego is in either case completely left out of the calculation, and therefore justifying his claim that the abstract ego is extra-physical. So to frame it in a different language, we have a system, say a spin. It evolves unitarily. We could then represent a measurement as a projection on that system with the measuring device and the abstract ego of the observer treated as, and the abstract ego treated as observer. Alternatively, we could unitarily evolve the spin and the measuring device, so now that they're maximally entangled, treat the abstract ego as observer, and so just do the projection on the measuring device.
No such thing as an abstract ego.
In both cases, the abstract ego is left outside the calculations and is thus completely irrelevant to the physics. And whether you say, oh, I'm gonna treat the measuring device and the observer as one system and apply the collapse postulate to the spin, or I'm gonna regard just this abstract ego, unitarily evolve the spin and the measuring device, and then collapse the measuring device, I get exactly the same probabilities. In other words, there's nothing that distinguishes those two cases. So in essence, this is his proof. You can imagine this chain of causation to be arbitrarily long, this whole sequence of entanglement. And you can always leave the observer out in the end. You can, sort of displace arbitrarily this cut between observed and observer without affecting any of the physics. But, at some point, the chain must terminate. And von Neumann is like, well, that just happens when you observe it. Without there being a cut, the spin, for example, is happy to be in 2 places at once. The experiment's not finished yet. The quantum state describing the world remains in a superposition of possible histories. Nothing decided yet. Now, to push back against this, to say that, the state collapses when it's perceived by the observer makes it sound like that's final or immutable afterwards. But from our previous argument, we know that's not the case because, like, for example, what if the spin and the observer who views that spin are themselves treated as a joint quantum system? They're confined in some sphere and we can completely control them. And, from some third person perspective, it's just yet another example of decoherence. It's like, okay, so, got simple spin and we got a complicated human being and, decoherence sets in and so forth. The observer, is in a mixed state of seeing up or down, but, if I was that observer, I would have to say that I really did see one up or down. But of course, even that is provisional because there could be some third observer that reverses time, undoes the interaction. In principle, it's possible, undoes the interaction between me and the spin, makes me forget what I ever observed, and restores the quantum coherence. So to say that, you know, the observer, so to speak, you know, collapses the state is not to imply that such a collapse is final. It simply says this. It's like if you're, you know, regarding, you know, yourself as like the experimenter, you can't necessarily what happens in your experiment until you fix the beginning and you fix the end. And for you, the end point of the experiment is when you measure the spin. Until you actually do that. Yeah, you know, someone could step in, they could, you know, undo this, do this, restore coherence, do a whole bunch of things, let beams recohere, make them go apart again, send it through gases or whatever. The saga's not over, the story's not over. What von Neumann's saying is like, if you want the story to be over for you, it's like you have to like take into account that like the story ends when you make the measurement, when you finally have made your decisions about what to measure and allow the thing to interact with, say, some measuring device, and you look at the result, etc.
So Matt, what does von Neumann say about before life existed, obviously interactions were taking place in the universe. Nobody was making measurements. Nobody was making decisions. How does von Neumann explain that?
Yeah, the natural, I would say, conclusion is that, in a sense, consciousness is bullshit, like in a way. I think that's the irony of treating this as a view that, you know, consciousness causes the wave function collapse, because it actually seems to imply that, you know, there is no difference between things that are conscious and things that aren't. Because just as you said, what about before there were, you know, human beings or things that we normally regard as conscious?
Consciousness is there's a causal relation between consciousness and wave function collapse, because wave function collapse is the product of measurement, and it's human consciousness that makes a decision to undertake the act of measurement. So there's a direct causal relation between wave function collapse and consciousness. It's not metaphysical. It's not metaphysical. And 1 second, it's not metaphysical. And the very notion that the observer is extra physical is pure metaphysics.
But
no
Victor,
such thing as something which is extra
that doesn't answer my question. There's no consciousness involved in an interaction.
I'm aligned with Mike. I don't think that it's a tenable position, the consciousness role. I think Richard Dawkins made a point of saying that, you know, presumably consciousness evolved, you know, through the evolution of species, and clearly there have to have been outcomes in order for evolution to have, you know, progressed. So there must have been, you know, outcomes, meaning like results of effective measurements before consciousness existed.
In what species does consciousness begin? Does a worm have consciousness?
You look into one cell
Where does
life forms.
Consciousness begin?
You look into one cell life forms and you find action potentials.
Yeah.
You find electrical signals moving through the one cell life form. You find an ability to actually perceive in a way without, this is perception, or the sense perception without sense organs. The ability to perceive
to their environment.
Water molecule and allow it to come in. The ability to perceive a sugar molecule and allow it to come in. The ability to expel waste because the cell has some sort of system for reading what the chemical composition of the waste is, and it expels the waste.
And most importantly, the ability to respond to a threat to their life. Single cells, hey, the coronavirus can respond to a threat to its life by mutating or in other ways.
No, it's not a living thing. A coronavirus is not a living thing.
Coronavirus is not what?
Viruses are not living things.
Oh, come on. Of course
They are RNA or DNA molecules with, for instance.
What do you think you are?
Not get.
For instance,
What do you think
protein
you are?
coats, with, for instance, protein coats and
What do you think
at
you
times
are, Victor?
some lipids that that need a host cell to reproduce. They are not living things.
All right, look, I've got Dr. Fauci on the phone. He confirms a virus is a living thing.
No, that virtually no one in the biosciences thinks that a virus is a living thing.
Oh, come on,
Virtually
Victor.
no one.
It's alive when it's in a cell.
It's RNA and DNA. What do
If
you
we could
think
move back to
you're
the
made out of?
topic that we were on with Matt.
It's a question of semantics, okay? That's the
The
question.
point is, it reacts to a threat to its existence.
I want to make
And that's how life
But this is
evolves.
like not the topic we were just talking about.
Can I make a subtle point here? Right? So one view about consciousness is that it's a thing, and therefore it must have an effect on things, and that therefore, if you follow, say like a natural selection kind of argument, one has to be like, well, what evolutionary purpose did consciousness solve, et cetera, et cetera, et cetera. Okay. There's another view, in a way, that looks at this issue about consciousness as being semantic, just like this question about, is a virus a living being? In other words, von Neumann, he doesn't really say that consciousness, causes the thing to collapse, like your consciousness makes a decision, and that's extra physical in the sense that can't be described by physics. What he says is that if you're you don't get access to those physics because you're you. You see what I mean? You're not, like, you have this perception, and then there's this thing that your brain is doing, and that's like in the objective world as far as you're concerned. So that the idea is that from your own perspective, you are extra physical, but you're perfectly physical from some other person's perspective.
That's not true, Matthew.
In other words, if can I just finish? A third person would, regard what you would regard as the extra physical.
Matthew, that's not true. Your brain, you don't know you're not aware of everything that's going on in your body, and your brain, different parts of your brain are not aware of what's going on in other parts of your brain.
That was just summarizing von Neumann's.
So how can you be outside of your own physical being?
Like, I would describe as this: your body provides your reference frame, but you don't perceive your reference frame. You perceive the world with reference to that reference frame, which forms a kind of background against.
Nature goes on about its business without us. Measurement is measurement quite often in the realm of quantum mechanics with a wave function collapse. It's a measurement of an instant in time. That is not the way the cosmos works. The cosmos is temporal. It is time unfolding. Time is space that is moving in place within itself in a fourth dimension. It is always occurring. It is even occurring in a black hole. And so there is no the undoing of time. So the wave function collapse, the act of measurement, are definitely products of consciousness. It's not a metaphysical relation. It's a causal relation that you make the decision to measure something. You've altered its nature by measuring it in a single instant.
The wave function is not physical. The wave function is not physical.
Wait. The one thing
what is physical is the quantum potential.
Even after you make a measurement, that measurement could be reversed by someone who can completely control you and the thing that you measure.
Well, I think there's another subtlety or distinction that should be made, which is that that there are really two kinds of barriers, two sort of thresholds, like the classical quantum. But even if we're just talking about regular non-quantum events, there's already an issue of where does my perspective, I have a boundary between myself and the rest of the world. Like, I am the world and the world is me, or whatever. Like this issue already exists before we choose to even talk about quantum mechanics. Like it's this problem in trying to describe things purely objectively. There's not really a good way to do it, because you always have to pick some frame to speak from, and to then try to have to work with that apparatus of description to talk about how quantum mechanics works, you know, is compounding the problem or whatever. So there are, what I haven't heard von Neumann or anybody distinguish is that there are really two sources of subtle, you know, ambiguity. You know, our own source of having no clear line of where I end and the outside of my perspective starts, and where the, you know, the so-called measurement apparatus ends and where the measured system starts.
And this ambiguity is all in von Neumann's mind. Nature does not have any ambiguity.
Is the thing
This
about
is all in von Neumann's mind.
Well,
and the inability of us to have an advanced enough mathematics, or maybe something superseding mathematics, to describe more accurately how the universe works. The universe doesn't use mathematics, despite what Max Tegmark and people like him believe.
So I would say, you know, I completely agree with what was said, in that even before quantum mechanics, you know, there were deep questions about the nature of subjectivity and objectivity, the relationship between first person and third person experience. And von Neumann was kind of excited that it seemed like quantum mechanics was providing a new spin, so to speak, on very old questions. Now, the thing that characterizes classical physics is the assumption of an objective world, which can be more or less understood, where the, you know, first person experiences of people in that world are really just sort of, in a way, you know, unmediated pictures potentially of what's really going on. When I say something like, it may be that all these questions about consciousness are really just semantic disagreements, similarly to how we define life, I would just say that we have absolutely no evidence of an external world. We have evidence of agreement between perceptions. In other words, no one has ever seen the world from a third person perspective, right? Everything always happens to somebody or something. In other words, it's not clear, you know, especially after the lessons of quantum mechanics, that the assumption of an external world per se, in the sense of existing independently of what anyone thinks about it, makes any sense, like, at all. But
then how do you explain neutrinos?
That's not the idea.
So Matt, how do you explain neutrinos and radio waves? We knew nothing. We have no perception of neutrinos or radio waves from our own senses. Our senses evolved to meet the challenge of survival for us, and that's how every species evolves. There's all kinds of stuff going on. There's all kinds of stuff going on external to us that we were not aware of until very recently, and I'm sure there's infinitudes of more stuff going on that we still don't know about. So what does our perception have to do with reality of what's going on in the universe? We have a very
I think you'd enjoy things a lot less if you didn't have one.
Because I think the idea is, if you want, I'm not saying, you know, you have to take this with necessity. I'm saying that the way that it makes sense is if you look at reality itself as an ensemble of perspectives. In other words, what we call reality is precisely what different observers agree upon, despite their different perspectives. But that doesn't necessarily imply that you can take an objective point of view irregardless of any perspective.
It's not what a dog would agree on.
When does consciousness arise? You know, is it the unicellular organism? Is it this organism? And so forth. It's really a question about, you know, how do sensory organs arrive? How do behaviors arise, and so forth?
And what about other species? They don't agree with us. Dogs can hear much higher pitches than we can hear, and birds can see in the ultraviolet range.
Sure.
So where is the consensus?
And bats have echolocation. all sorts of
Our
animals migrate on
consensus-
the basis of the magnetic field, but we have, as human beings, devices. But these devices
but we
are,
have, but
one
it's
second,
still
one
limited.
second, one second, one second. These devices are a form of prosthesis.
Yeah, they're limited. And you know, Abraham Lincoln.
One second.
Yeah.
They extend beyond us. And as a result of extending beyond us, they become the equivalent of a kind of third person perception of the world that we have a window on when we look through an X-ray telescope or a gamma ray telescope. When we are able to see, for instance, in infrared, and we're able to see in the manner of a viper. Okay, we're able to see in the manner of other species. Because of our devices, we actually have third-person experience.
And it is still a very limited perspective. Do you know that Abraham Lincoln was almost convinced to close down the patent office in the 1860s because scientists agreed that everything had already been discovered and invented? What would be the point of funding
the first time I've heard Abraham
office?
Lincoln's name mentioned.
And by the way, Trump has the same philosophy, but Trump is not as smart as Lincoln. That's the problem. Lincoln was more open-minded.
You said something I agree with. There's another thing that is more to the point with.
Is that the first time, Michael Fishman? Is that the first time?
It's the first unequivocal one. Yeah.
Oh, okay.
At least Victor and I agree. Victor and I seem to agree.
I wish Trump were unphysical.
Victor seems to be a black hole. Why is it, Victor? Why don't you show yourself?
I mean, so if I can
he appears in the infrared only.
Are you a Martian?
I would say like the parallel,
Let's give it a Martian
parallel thing, which is what we were actually talking about before. I remember when you mentioned this, Matt, several meetings ago, and I was surprised to learn that von Neumann had this section in his book, which is basically, I feel like, not widely read because the typesetting is like pre-latex. And,
it's really
you know,
true. It's a very book to dig.
Yeah, it's really annoying. Like no one ever recast that. But anyway, so I was looking at it, and I was kind of curious, like, what is this phrase? He kind of mentioned this psychoparallelism, whatever it is, as though this is like a phrase that is in vogue and that I actually know what it is. And at the time, I suppose that's the case. But so I was looking a little bit more, and maybe you could fill in where I stopped.
Yeah. So
my sense is that this was a school of think. I'm sorry, that the particular assumption by whoever was the guy that started with pioneered this, or like with the father of that, that we have consciousness, like consciousness is physical, but it sort of operates in a separate, like it's decoupled basically from anything not conscious, and it's like somehow things were like synchronized with the physical non-conscious stuff in the universe, like at its origin, and our conscious experience is in sync with everything going on around us that's not conscious, despite having no interaction really, because of some initial amazing synchronization of these two.
The only reason we put consciousness in a separate category is because we have not been able to explain it.
I just asked a question that was not so trivial to formulate.
Okay, so yeah, so like in the mid to late 19th century, psychophysical parallelism became kind of like a hot topic, especially in the German language speaking world.
And so did phrenology and eugenics.
Okay, so one of the
Matt, would you come on? Let me speak. Would you allow Matt to? I'm sorry, Matt. Would you mind sort of stating how you interpret the meaning of that term?
So one of the things that happened was the invention of psychology as an academic subject, in the mid to late 19th century. And so people like Fechner and others began to do the first so-called psychophysical experiments. And they were things like, an attempt to apply quantitative analysis to perception. So like, what are the closest two tones that someone can hear? What's the faintest sound that someone can distinguish from another sound? Like, what's like the most amount of touch that you can feel? And they, found certain mathematical regularities relating to, say, the amount of force applied and, the perception, say, of like pressure difference, because they would start asking people questionnaires, did you feel more pressure then or now? And so people began to try to develop a kind of quantitative science of perceptual experience. And, you know, this sort of gave birth to, you know, the sort of various phenomenological schools of like German philosophy, which, you know, were more or less influential in different ways. Now, okay, so with regard to the sort of interpretation of psychophysical parallelism that you gave, I would sort of like argue a little bit with it, because I think what they were trying to get at was this, right? Descartes, in separating mind from body, made classical physics possible, so to speak. It was like, okay, we can sort of simplify the world. We'll just like ignore all the mind part. We'll describe the world entirely as body, and then we find that it's, you know, governed by these like mathematical rules. So a very like productive thing to do in science was to, you know, ignore any quandaries about perception and just study the regularities of the bodies themselves. In the 19th century, though, I mean, people were kind of going back and forth. Like on the one hand, you had like the Kantians who were suggesting that we should look at time and space as sort of modes of our perception. And so now there's like a sort of idea that, you know, depending on like what we are, you know, we're going to perceive the world in different ways, and we can't just disregard like the mediation of perception. And this comes sort of with a certain degree of stakes in a different way, because in the mid-19th century you have the introduction of Darwinism and natural selection, which, you know, spreads like wildfire and changes people's view of the past. And so now, like, you have this view of like, you know, all the organisms are kind of, you know, related to each other, and they're evolving, you know, from these different, you know, simpler organisms, and their sensory apparatuses are, you know, evolving and so forth, and under evolutionary pressure. And it's sort of a question, well, you know, how does Kantian philosophy apply to a sea urchin or to a fish, right? Like, how does the evolved body of an organism relate to its inner world of perceptions? And, you know, this was like the sort of animating theme of these nascent fields of psychology and in philosophy phenomenology in the mid-late, you know, 19th century. Now, the psychophysical parallelism view is basically says this: the problem with the whole mind-body thing, if you think about it, is that any possible explanation kind of has to stick with the body part, right? Because, you know, you might think about it that what we mean by an explanation, right? The definition of an explanation is that some things happen in the physical world, and that's why this happened. In other words, if I want to explain why did I see the color red, and like, why did I think this thing? The explanation can only take the form of, well, some photons entered my eye and then these neurons fired. And so the explanation consists in a story, you know, that takes place like in the physical world. But at the same time, we don't have direct access to the world outside our perceptions. We only have access to our perceptions for whatever reason. Therefore, we can't simply reduce mind to body, even though an explanation consists in explaining why we have a given perception with reference to a body, because for us, the perception always comes first. So therefore, they were wary of a sort of completely materialistic view that reduces mind completely to body, but they didn't want to give up the principle that anything that happens in the mind can be explained with reference to bodies. So they wanted to have their cake and eat it too. They wanted to kind of flirt with what is often called idealism, but without getting trapped by solipsism, the view that you're a kind of God and all this is just an arbitrary hallucination of your consciousness. So as I say, they're interested in a view of the relationship between mind and body, which both treats them as irreducible or not reducible to each other, in the sense that our perceptions for us always come first. And therefore, any science is, in practice, a comparison between experiences, but without getting any bogged down in sort of soul type crap, or like this idea that like there could be any explanation for what happens in the mind other than physics. So they want to have their cake and eat it too. And so von Neumann is like, holy shit. I mean, that's what people were saying in the 1870s. And like, it just seemed like kind of a cool thought, but like, whatever, we have like Newton and this like deterministic classical physics and blah, 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 whatever. And then von Neumann's like, holy shit, we discovered quantum mechanics and it's like completely compatible with this whole psychophysical parallelism thing.
May I just pause before you jump to the von Neumann point? At the time that you were just describing the views, was there an attitude that there's something unsatisfying ultimately about the state of people's ability to describe, like there's something unsatisfying about that philosophy, or like it's unsatisfying yet final, and unsatisfaction is somehow intrinsic to experience with description? Like how did they view the state of their art as being like towards complete or incomplete?
Well, again, like as I say, they were inspired.
Well, that's a satisfying picture to people, or was there something just like?
Yeah, so
you say again, but I don't believe I heard.
They're worried about. I think part of the motivation for the whole thing is this idea that like now they want to consider the inner life of animals and stuff like that. Well, which they are sort of forced to consider by, this emphasis on Darwinism. And, everyone's being influenced by Kant, who's, always emphasizing the degree to which our experiences are shaped by certain forms, certain structures, like time and space. And so people were like, well, if Kant says, oh, time and space in the way that we normally think of them are the fundamental forms of perception, well, but what if this animal evolved a different kind of sensory apparatus and interprets the world in a different way? Is that a way of disproving Kant, who says that all observers necessarily see the world in this particular way? So there was like a sort of attempt to like democratize the idea of like Kant's sort of like fundamental forms of perception. But again, recall that like what's happening is the beginning of psychology as a quantitative science. So you have all these people like doing these experiments in perception, and it's like being able to quantify things about like our perception of sound and our perception of touch and our perception of color and stuff like that. So that we seem to be able to like find mathematical regularities that govern the relationship between perceptions and stuff like that. But of course, at the end of the day, the big question is something like, well, if the world is just this objectively given thing that, exists independently of anybody or whatever, then why is it that we're us? Why is it that, like, as far as anyone knows, people only have a first person experience? And in a sense, logically speaking, the idea of experience presupposes someone having that experience.
I'm all for depth of the inquiry and history of philosophy and history of ideas, but how are you specifically making any claim on behalf of von Neumann and of the validity of this view of psychophysics, which would be the term that can be applied to the observer specifically within quantum mechanics, to take us out of the realm of the history of ideas into the realm of the application of the idea.
Right. So
Well, sorry, I guess I inspired that. So, but
no, that's
okay. That's okay.
So like the way that I would sort of, I guess my take on the way that this would suss out for von Neumann is to say something like, so there's a bunch of quantum states, that's the world. And I'm interested in, say, me. I'm an observer, right? So I make this cut. I say like, all right, here's Matt's quantum states of his body, and here's the stuff that's like outside his body or whatever, okay? Make that cut. Now, that is from someone else's perspective. In other words, not my perspective, right? So someone else, like your guys' perspective, you see me as a body, like you see me as like this face and shit, right? You know what I'm saying? So there's Matt's quantum state of his body, and there's like the shit that's outside of Matt. And they're just these two quantum states, and maybe they're entangled like that. But the idea is that, like, if I was me, then that thing that you regard as my body is my reference frame. It's like, I don't perceive it. It is with reference to that I perceive the world. In other words, you know, it's like what you regard as the quantum state of my body is like providing me perceptually, so to speak, with like my XYZ reference frames. Like, you know, when you just imagine in your head, like, oh, here's a sphere or whatever, you know, you're just thinking about it, and implicitly you've chosen like an orientation for that to be at or whatever. And so, you know, I think the view is sort of like, from your own perspective, your quantum state is extra physical in the sense of it's not part of your theory of physics, it's your reference frame. It's the invisible background against which the drama of the world like takes place. But from another perspective, that thing which for you is extra physical is perfectly physical. It's just, you know, the quantum state describing your body and all your sensory apparatus and shit, and then the rest of the world. And so what von Neumann shows, you know, is like when you consider these sort of measurements situations where, you know, you sort of have a particle and a various chain of this gets entangled with this, gets entangled with this. And, you know, I can, and I'm worried about like when the supposed collapse to a definite outcome occurs. Does it happen at the beginning, at the end, in the middle? In other words, it's sort of a question of, if I regard the collapse as happening at the cut, where I've said, oh, this is the boundary of Matt's body or whatever, what he shows is that the physics, the probabilities for the outcomes to experiments doesn't depend where you place the cut for any given experiment. And so therefore, although, you know, the physics has to be described from some observer's perspective, the physics in itself is independent of where you draw the line between subject and object.
So I wonder,
does he ever make, I'm sorry, go ahead, Michael.
I was going to ask, it seems like the situation is more that there's not going to be any clear answer to a question about where it happened, but because it seems like in any real situation where you try to put a cut somewhere, like that's going to actually involve putting material stuff somewhere to look, you know, and that's going to now, you know, like the whole thing about it, if you try to stand behind the two slits and with flashlight and see which one the electron's coming out of, you don't get the interference pattern anymore. So and so clearly, if just moving myself with a flashlight up to behind the slits, if that's like putting a cut somewhere, that clearly is really affecting what happens. So it's not, you know, irrelevant. It's like somehow you want to. It's more like what you were saying earlier, where you don't know at what point in between the magnetic field and the exit where the one beam became two. But it's like it seems like it's more in that inaccessibility of knowing more about that.
If I understand you correctly, yeah, this is like an important point. So it's like what von Neumann is saying is with regard to like a single completed experiment where you've decided what happens at the beginning and like what happens at the end. And once you fix the beginning and the end, you can regard the collapse as taking place like at any point along the history. And so
it's kind of like a retrospective attempt to explain or to have a narrative. It's arbitrary.
It doesn't happen at any point in the history. It happens at the point of the measurement, in the instant of the measurement. So there's no
don't have to assume that.
no ambiguity there. As far as the cut is concerned, there is no place to make the cut, because at this very moment I have within me water molecules from every single body of water in the world. At this moment, I'm breathing in air molecules that virtually every single human being in the world will breathe during a lifetime. I mean, I have within me not only my DNA, my parents' DNA, I have within me the DNA that derives from the very first life forms, assuming they did arise, you know, in the deep sea vents. I have within me DNA from those very first life forms. So there is no distinction whatsoever between me and the world. No cut is possible. And as far as the outcome is concerned, the outcome comes from the precise instant of the measurement. It's not arbitrarily deriving from the history that preceded it. It occurs from the measurement.
Well, what I'm saying is that mathematically, you can treat it as taking place not at necessarily the instant of measurement, but any time in the experiment. In other words, here's like
in what sense?
In the following sense. So it's like, here's like a spin, and then it's gonna go through like a bunch of things, okay? And then suppose I say, all right, I'm definitely gonna measure where it is, and you know, it ends up like being here, okay? So
but it's that vertical line that's that's important, not the point on the line.
Right,
it's that instant in time that's important.
Right, but that's
the point where it lands.
If that happened, right, I could say, oh, well, actually, the cut happened here. And, you know, I got that definite outcome. And then because of the linearity of quantum mechanics, then, you know, that it just stays that outcome along each of these paths. Like, it always takes the up path. And of course, you get that result. But I could have also imagined it takes both paths here, and maybe it collapsed here, and then continued along its merry way, and then got that. Or maybe it was here, or maybe it was at the end.
Well, if you really believe in, if you really are a Copenhagen follower and you believe in superposition, then you believe that it was the instant of the measurement that led to the outcome, not that it was in a state and it continued in that state. You're claiming that superposition is always the condition, that you're in this state of indeterminacy, and the determination comes from the act of measurement. So you're describing, which school are you following here?
Well, I think there's a difficulty with pinpointing when was the measurement precisely, right?
Correct. I believe the correct understanding of this is that, look, see, I fixed a beginning to this experiment, and I fixed an ending to this experiment. And the idea is that mathematically, it's like, okay, I have this projection operator that's gonna like project it to like the up or the down state, right? With a certain probability. Given this history from like beginning to end, I get the same results if I like apply the projection here and then it imagined, you know, because if you regard it as going in a superposition, right? It's following out both paths and the evolution is linear. So in other words, if I like cut out one of these paths, then it just takes the one path. Or if I cut this path off, it takes this path. Or if I leave it both open, it takes both paths. I can imagine the filter happening here, or happening here, or happening here, or happening at the end, and I get exactly the same result. But
you're only going to get exactly the same result in the sense that if the probability is 50-50 up or down, that you're going to get one or the other at that one moment. But if you believe that superposition is really the condition that has been following throughout, it is the state that you have coaxed it into through the act of measurement in that instant that is determinative. But if you believe that it's that we're in a deterministic universe, and the reason that the probability is 50-50 is just that, you know, we're talking about a binary system, up and down. So one of the outcomes is a necessity. So I don't know what I don't know how you can say that you can foresee the outcome as being, you know, a spin up 2/3 of the way through the trajectory or 1/3 of the way through. I don't understand how you're saying
Right.
that.
This is the fundamental issue. It's like, so there's like an ambiguity. It's like if I regard, so here's the end of the experiment, the beginning of the experiment. You're perfectly within your rights to regard that collapse as happening at the instant of the experiment. But it's just ambiguous because you can get the same result if you imagined it collapsed over here, over here, over here. In other words, if something follows both paths and then you ask which path it took, that's just the same as, you know, deciding it took the one path at the very beginning and then just took that one path. Because what it means for them to take both paths is for them to just follow it in parallel. The difficulty comes when you consider a different experiment, right? If instead of measuring, you know, where it came out, I do my thing where I recohere the beams, okay? Then I have to say, no, the collapse didn't happen here or here or here, it happened nowhere.
Well, we know for a fact, listen, you're acting upon a physical process in some way, either with your own body or with your device, with your measuring device. You're acting upon it, and therefore you are altering it. So this is a causal relation. So if you're going to believe, you know, you can believe. I see a way to have all the possibilities and probabilities retained without superposition. What you've got is at any moment in time in a physical system is a series of evolving states, right? And so without there being any superposition whatsoever, you know, I choose a certain moment to make a measurement, and whatever the state is of that object without superposition, that's what I'm going to measure. So
I think then the question becomes, what does it mean to have a state that's in a superposition?
It's exactly right, though.
I think the superposition is metaphysics. That's what I think it is. I think what you have is the cosmos, which is always in time, is always in an evolving state. And so when the act of measurement, forgetting indeterminacy, forgetting quantum mechanics, the act of measurement measures the state at the instant of the measurement. Now, the instant of the measurement is not without dimension. There's no such thing as a dimensionless point in time. It is a nanosecond or a picosecond or a femtosecond. It is some span of time, and it's at that instant in time that's not an instant. That tiny span of time, that's what the state that it was in, that's what I measure.
Look, I just want to distinguish between like two different experiments, right? One experiment is particle goes through a Stern-Gerlach and gets entangled with this. At each moment of time, there's like two ways it can go. And, you know, then at some point we recohere the beam and then, you know, measure it in like a Stern-Gerlach apparatus, okay? And then there's this experiment where it goes along, da-da-da, and then we just measure the position without allowing them to recohere, okay? In this case, I asked the question, in the first case, when did collapse take place? okay? I can say this much. It took place after this point. It could not have happened beforehand, because if these two guys recohere, it must have taken both paths. Therefore, there's a limitation on where I can regard collapse as taking place. I can't regard it as having taken place before this point. Afterwards is fine, you know, I make a Stern-Gerlach measurement, you know, and then say, oh, it was up, all right? And then I could be like, well, wherever it happened, it took place after this point. In this other experiment, particle goes off, two paths, and then we measure it. Don't allow them to recohere. In this experiment,
when we're talking about spin,
really just finish.
we're talking about spin, I mean, forgetting trajectory, forgetting paths. When we're talking about spin, we're not talking about two possibilities. What we're talking about is perhaps an infinite number of possibilities, because you're talking about any position, any vector coming in a direction which is downward from the horizontal of the measuring device. That's what spin down is. So it's an infinite number of, potentially, an infinite number of possibilities down positions and an infinite number of possibilities of up positions. It's not an either or. The either or is just that is how simplistic our measuring capability is.
Okay, well, if
Victor, it's
like,
there's only two possibilities, up or down, and it's determined. Spin. A particle is forced into a spin position. This is where we diverge on, you know,
No. That is not what spin is. Spin. When you talk about spin up, when physics talks about spin up and spin down, it is not. It's not an either or. It's a position above the horizontal is up. Any position on any vector in any direction.
No. Spin up or
that
spin
is what
down.
it is.
Let's consider the spin regardless of position. Let's not even care about where it is at all. What I'm saying is this. You start off with like a superposition of like up and down, and then say it becomes maximally entangled with another spin. And now it's in the state up, up, plus down, down. And then it gets entangled with another spin. And now it's in the state up, 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 plus down, down, down. And then it's entangled with another spin.
Wait, Matt.
Up,
You can't
down,
have three particles entangled. You can't have three spins entangled. You can only have two spins
perfectly
entangled.
valid state. Two quantum particles can be maximally entangled only with each other, but
right.
particles can be non-maximally entangled.
But not the spin, because spin is either or. It's either up or down. You can't have. Where does the third particle come in? You're right. Everything is entangled with everything else.
I'm saying,
but not spin. Spin can only be two particles entangled.
You take. There's a you'd have one spin and then unitarily evolve it to be in the maximally entangled state of two spins, 1, 1 plus 0, 0. And act on another spin, and now it's get the state 0, 0 plus 1, 1, 1. This is perfectly standard.
Entanglement is a complex system. Entanglement doesn't mean perfect correlation. There are degrees of entanglement between the various quantum properties of two particles and of arrays of particles.
You can only have two particles entangled. You can't have three.
Yes, you can.
How does the third one come in? What determines what the third one will be?
They interact from a certain distance and they become entangled.
No. But if you have A and B, if you measure one up, the other one has to be down. Where does the third one come in? What does that have to be? Somewhere in the middle? Come on.
No.
When it comes to spin, you can only have two particles entangled. Yes, in general, you can have everything is entangled. Everything in the universe is entangled.
Manifestly false, okay? If I measure a particle that's like entangled and I collapse it to a pure state, it's not entangled anymore. You can have non-entangled stuff, you can have maximally entangled stuff, you can have kind of entangled stuff.
You're right. Once you make an interaction, disentangles stuff.
In Michael's philosophy, it takes two to entangle, and you can't go beyond that.
No, you didn't hear. I repeated it 3 times, Victor, and you didn't hear me. I said only with spin.
I thought that was
only
fun.
with spin. Maybe you'll hear it the 4th time.
Joking,
Only with spin can you only have two particles entangled spin-wise. Where does the third one come in? If you measure A, we know what B is. Do we also know what
Why?
C is?
If you measure,
Wouldn't like a
Meister.
Bose condensate be like an enormous number of spins entangled?
Exactly. Thank you, Michael.
You know,
No problem.
again, you didn't hear what I said. I
Did you
agree
hear what
with you.
Michael? Did you
Everything
hear
is
what Michael
entangled
Fish?
to some degree.
Did you hear what Michael Fishbein
But
just
not-
said about Bose-Einstein condensates?
Not their spins. Not their spins. You can only have pairwise entanglement for spin. For any other characteristic, yes, you can have multiple particles entangled. But spins can only be pairwise entangled.
Moshe have to say, where the hell is Yahweh?
hey, wait, I forgot about Moshe.
Oh, I got Dr. Fauci's on the phone about viruses. 2 viruses cannot be entangled.
The thing that we're alluding to is the so-called principle of like monogamy and entanglement. And the idea is that
Hey, don't get fresh now. This is a family hour.
if you have
4 hours.
3 states, A, B, and C, then like A and B can be maximally entangled. But if that's the case, then A and C can't be. In other words, you can have tripartite entanglement, that's fine, between 3 particles. But you know, if 2 particles are maximally entangled, they can't be maximally entangled with some other particles.
Yes, but spin can only be a maximal entanglement. That's the point.
That's not at all a thing.
Other particles can be partially entangled. But with spin, you can only have them pairwise entangled. You can't have 3 particles entangled with regard to spin.
Yeah, you can.
Is it true that, like, can we think of degree of entanglement as meaning if, say, 2 particles are entangled, we talk about how entangled they are. If I measure one, that act of measurement, the degree to which it constrains the possible outcomes of a measurement on the other one, that degree of
we're talking about
is
spin
entanglement.
limited to spin.
Yeah, so if you have 3
if 2 particles are entangled spin-wise, they are maximally entangled spin-wise. How can you bring in a third particle into that entanglement?
Michael, you're talking very loud.
You are
very loud.
I'm sorry, but it's just wrong. It's just wrong. Look it up in any textbook.
Okay, but just a little calmer.
Spin can only be pairwise entangled, and it's always maximally entangled. And when you make the spin measurement, it becomes disentangled.
I genuinely have no idea where you heard that, because, like, you can have spins; they can just be entangled.
I'm not familiar with that.
If you
can't have 3 spins adding to a spin, 3 spin 1/2 particles summing to a spin 0 state and doing the nice clean, like, anti-parallel.
Yeah, if you're talking about being in an anti-symmetric state, if you're talking about, you can't have 3 spin halves in, an overall spin 0 or a 0 angular momentum state, that's totally true, if that's what you mean. But, if you don't care about that, yeah, sure, 3 particles that are 3 spins can be entangled, and you can think about that like for every state of the one guy, there's a linear map to states of the other 2 guys. And a linear map from states of the 2 guys to states of the 3rd guy.
You're talking about states. You're not talking about particles. You're not talking about spin. Spin is a very specific type of state.
I believe I see what your confusion is. You're thinking about the anti-symmetric state, right? Like up, down, minus, down, up for 2 spin half particles. And that's an angular momentum 0 state. And if the one guy's measured to be in a direction, then the other guy, if you measure in the same direction, will always be opposite.
Right.
3 spin half particles, there is no such state because there's
any way to turn down everybody's volume at once? Because I'm looking for a way to turn. This is like blasting my ears.
Okay, here, I'll back this up a little bit. So that's perfectly true. But if you could have 4, suppose you had 4 spin halves, the angular momentum 0 subspace is 2-dimensional. And in fact, next time, we're going to see how that entangled state can be interpreted as a quantum tetrahedron, where the 4 spins are like the areas of the faces. So, the thing which, we didn't really get to today, but we'll pick up later is exactly that. We're going to be talking about, the addition of angular momentum and exactly this issue. You have the tensor product of spins with different J values, and you want to decompose it in the basis, in the total angular momentum basis. So for example, what we'll see is like, if you have 4 spin half particles, the, spin 0 states, there's 2 of them. And so they can be parameterized by a qubit. And there's an interesting relationship to the conservation of angular momentum and the closedness of the polyhedron that they represent. And so we're going to talk about that. You can think about this tensor product of 4 spin halves with the angular momentum constraint as representing an interaction vertex that conserves angular momentum, so that you have these 4 spin states, and if you have like an incoming spin that gets contracted with one of them, the 3 that pop out are going to have exactly the same angular momentum that the original spin coming in had. And that is what leads to the theory, actually, of loop quantum gravity in its origin. We don't have time to start that whole discussion, but that's kind of what we'll do next time. But no, but to get back to my main thing here, I just want to leave you with this thing, right? Here's like 2 experiments. This one experiment, you have, this sort of like maximal entanglement being created by like yet more 2-state systems, taking both paths, and then the beams are rejoined and coherence returns. And therefore, in this experiment, if a collapse occurs, there's a constraint. We're forced to say it happened after this point, because the only way this recoherence makes sense is if that particle took both paths. But that's a different experiment than this. This is the experiment where it goes off, takes both paths, and then we just measure it. In this experiment, we end up with this like, maximally entangled state, all these guys down plus all these guys up. And therefore, we are perfectly allowed to regard this collapse as taking place here, anywhere, up to this final point.
I just can't buy that idea. You keep repeating it, but it just doesn't make any logical sense.
All I'm saying is that if you multiply this state, like at this point and like project it and then evolve it, or if you project it here and then evolve it, or if you project it here and evolve it, you'll get the same answer, the exact same numbers.
Have you turned into bone in the last, half hour or something?
What I'm saying is that quantum experiment you have to specify the beginning of it and the end of it. And once you've done that, you can then ask, given the extent to which things cohered or recohered, to what extent is the boundary line between, observer and observed, or where this projection takes place, to what extent is its placement arbitrary? Indeed, von Neumann doesn't say it's completely arbitrary. He says it's arbitrary to a very large extent. In this case, it's completely arbitrary. Could happen here, collapse happens here and then unitarily evolves, or collapse happens here and then unitarily evolves, or it unitarily evolves all the way and then the collapse happens at the end. We're completely free to multiply our projector at any point and we're gonna get exactly the same answer. Here, we're free to displace the measurement somewhere over here, but we can't regard it as happening down here because here we're forced to regard it as taking both paths because we've allowed it to recohere. There's no contradiction between these 2 views because these are 2 separate experiments. And quantum physics doesn't allow you to really say anything until the beginning of the story and the end of the story are fixed.
You do realize that Schrodinger's cat, you know, the two states that are not determined, you know, until you actually observe what has happened inside the box, that this is a cosmological joke.
Yeah, I mean, it was meant as a reductio ad absurdum kind of argument. Like, this is like why we can't apply superposition.
Yeah, well, this is why, I mean, you know, Schrodinger thought that quantum mechanics was incomplete.
Sure.
Dirac thought that it was incomplete. Einstein thought that it was incomplete. Many of the founding motherfuckers of quantum mechanics assumed that it was incomplete. So
it's not
somebody's
incomplete.
hungry.
It's misinterpreted.
Well,
By
If
some,
you do
yes.
the math, if you do the math differently, it is complete. And that's what Bohm did. That's why I suggest that you look up Bohm before you start, you know, expressing his opinions.
I'm not.
It's not incomplete.
I am not denigrating Bohm. So just don't worry about it.
But what I'm saying
Don't
is
worry
there is
about
a missing, you know, Einstein talked about missing variables or hidden variables, but he
Right.
was wrong. He was looking for external hidden variables. What Bohm showed is that by solving the Schrodinger equation, the same Schrodinger equation used in Copenhagen, by solving it differently, you come up with the quantum potential that one of the gentlemen mentioned before.
Okay, as far
it's there all the time. It's just that the way Copenhagen solves the equation.
I do not
keeps it
agree.
hidden.
I do not agree with the concept of hidden variables in the specific context that Einstein was using it. But
Yeah.
the notion,
But I'm
the
saying
notion,
there was a hidden variable, but it's not hidden in his context.
1 second.
Yeah.
But the notion
Yeah.
that we have actually had a loophole-free Bell test is nonsense. We have closed the loopholes on locality and detection. We have not closed the loopholes on setting independence and free will superdeterminism. So we have not, there is no such thing as a loophole-free test in any realm.
Well, what's free will superdeterminism? Is that like everything was determined at the beginning of time?
Yes.
Okay.
Yeah, like your very decision.
I think it's true, but
what the particle's going to do by some cosmic fiat at the beginning of time.
Not cosmic fiat, not cosmic fiat, by the nature of things unfolding in the way that the nature of things must unfold. It's not by fiat. There's no direction occurring.
And
it's by the laws of nature.
And nature doesn't give a damn about our inability to explain it accurately. All this probability and superposition bullshit has to do with the fault of our mathematics, which, by the way, has been corrected, but it's not taught for political reasons.
In that, there's an article by Dirac that's included in that Xavier University thing, because he gave it as a lecture there. And it's like a kind of a resume of like different issues in quantum physics, kind of an overview. And he kind of is like, divides questions about quantum physics into like two groups. You know, one group is, you know, interpretative issues, like it's unclear about this measurement thing, or like the observer, like et cetera, et cetera, et cetera. And then there's mathematical questions, or empirical questions even, that we just don't know how to answer yet. Like at that time, it was like, how do we make sure to have a completely consistent relativistic theory? Or, you know, like today, it would be like, what about quantum gravity? You know?
Do you believe in quantum gravity? Where's the empirical evidence? No empirical evidence, zero, that the graviton even exists.
Not discovered until there was the technology.
Discovered? The graviton has never been discovered. Where's the quantum gravity? As far as we know, Einstein's theory is the only valid theory. To extend quantum field theory to gravity is a quantum leap. There is no physical evidence for it.
So that's why we have several competing theories, because there's a vacuum of experimental evidence.
Einstein's theory.
Thank you, Karl Popper. But there are other epistemologies beyond Karl Popper.
So, you know, the original quantum stuff.
There's no physical evidence for a quantum gravity.
Discovered when we could do experiments like Stern-Gerlach apparatuses and stuff, right? Today, it's like, what are the comparable experiments for quantum gravity? The scale involved are very, very tiny.
No. But we haven't discovered the graviton. When they did the Stern-Gerlach, they had already discovered the photon and the electron and other parts. We have not discovered the graviton, and physicists talk about it like, oh, of course it exists.
Well, but you know what they're solving that.
Show me a graviton.
Right.
Who
So
Most physicists are not in the business of that. They're not in that kind of physics. It's pretty obscure even within physics.
They're in the business of science fiction.
The assumptions of the theory lead us to assume that it will be exceedingly difficult to find the graviton if we ever find it. Look at how long it took us to uncover.
Well, ain't that
one second.
Yeah.
To prove the existence of gravitational waves. The existence.
No,
one second. Let me finish. The existence of gravitation.
You're wrong, Victor. Gravitational waves are explained by Einstein's theory. They don't involve gravitons.
Because you speak louder doesn't make you right.
Yeah, but you're wrong.
Just be quiet for a second.
Yeah.
For a second. It took us nearly forever. It took us till very, very recently with LIGO to find gravitational waves, whatever, through the collision of two black holes, the collision of two neutron stars, the collision of a black hole with a neutron star.
That's not a quantum theory. That's
Einstein.
Nonlinear general relativity.
Wait. So the existence of gravitational waves seems to point to, in terms of our understanding of, the relationship between waves and particles, which is incomplete. Let me finish, damn it. Seems to point to the distinct possibility of the existence of the graviton, because the waves themselves seem to contradict, to a degree, general relativity.
Victor,
you're completely wrong. Einstein's classical
I also feel like you're shouting.
General relativity theory.
I would say that if there's no graviton, then that becomes an interesting question itself. Why is there no graviton?
Well,
it's not something that's, I don't know why you see that as an obviously natural thing.
It hasn't been discovered.
We know
the reason we're supposing a graviton is it's an extension of quantum field theory, where there is a spin 1 particle that mediates the
fine, but the point being that currently there's no known for sure realm that does not operate governed by mechanical rules.
Based on evidence. So then science is based on physical evidence. We could talk about math, or we could talk about science.
Yeah,
science is based
on
physical evidence.
Today is a day in July. Like, these are not.
Tell me who discovered the graviton. And by the way, what Victor said about gravitational waves are a nonlinear phenomenon of classical general relativity. It has nothing to do with gravitons.
I forgot what we were talking about before.
Michael S. By the by, the graviton is theorized as a spin 2 particle, not as a spin 1 particle.
That's true.
I just explained to you why it's theorized. It's an extension of quantum field theory, and there's no evidence that. Where's the physical evidence?
Right,
that's what science.
What physical evidence did we have for the existence of the Higgs particle? How long did it take us to uncover it?
Yeah. Okay.
Well, the graviton is the most difficult particle to possibly uncover, according to the theory itself.
I agree. So here's the thing. Last summer, I went to a Loop quantum gravity conference. And, the issue of how to resolve these theoretical issues with experiment was like a really important one for them, right? Because they themselves, like as a field, want to distinguish themselves from string theory, from, the ADS CFT stuff, like all the different competing theories of quantum gravity. And the consensus was that, like, if there's going to be in the near future evidence for or against different theories of quantum gravity, it's going to come from the observation of large-scale features of the sky. In other words, your theory of quantum gravity is going to tell you something about what happened, maybe something involving inflation, something involving, being able to predict from very tiny quantum effects in the early universe, large-scale features that we observe by astronomy. And it makes sense if you think about it. Like quantum mechanics was discovered in the 20s because the technology had gotten good enough to do these experiments one photon at a time, one particle through a Stern-Gerlach, et cetera, all these things. Today, you know, you look at like, you know, where is the technology progressing? On the one hand, it's the ability to control multipartite condensed matter systems. And on the other hand, our fucking insane ability to do astronomy. Ever more fancy telescopes, ever more fancy neural networks processing all these high resolution images for the first time, actually being able to test things like, does this quantity look the same in all directions in the universe? Or are there inhomogeneities that can be explained only with loop quantum gravity, or only with this version of string theory, or only with that? So for several decades, we've been in a position with regard to quantum gravity of, you know, trying to unify, you know, different parts of physics that we know, you know, whether it's, you know, deriving the Hawking radiation from, you know, quantum field theory and curved space-time, or, you know, thinking about, you know, the theory of spin and kind of generalizing it to these spin networks and spin foams and loop quantum gravity, all these different things. At the end of the day, you know, they can only, they're each plausible in their own way, and they, in the end, can't be decided, you know, unless we get experiment. And that's why we're in this uncertain situation. And, you know, I think that precisely because, you know, the quantum gravity effects are so faint and so tiny, it's, you know, most people working in the field today think that the distinguishing evidence, you know, for one theory or another is going to come from cosmology and astronomy. Okay.
I mean, it's by far the weakest force. It's exponentially weaker than any other force. So it's naturally going to be the particle that is the boson, assuming its existence, that is by far the most difficult to find. Okay, think of the mass of the Higgs. Okay, and yet how difficult it was to find the Higgs. It took us a half a century to find the Higgs, for God's sakes. So I mean,
well, then the measurement of gravitational waves, albeit those are not gravitons necessarily, is still extraordinarily so impressive, and was not a foregone conclusion that was achievable, that level of precision.
Here's the thing about the Higgs. There are serious scientists who dispute that the Higgs has been discovered because it was based on statistical analysis, statistical blips in the curve measured at the LHC. I'm not going to argue that point. But again, gravitational waves are a nonlinear phenomenon of Einstein's gravitational equation. It's a completely classical phenomenon. It's not a quantum phenomenon, regardless of what you may have read in the popular literature. And until somebody, I'm not saying we shouldn't look for a graviton, but it's very convenient. It's very convenient that the people who believe in gravitons say, well, there's no chance of finding it because it's at the Planck scale. We would need an accelerator the size of the galaxy to find it.
Well, to rest assured that the amount of funding available for that research is so minuscule that there's not an excess of activity.
How convenient it is for people to come up with a theory knowing it can't be tested. That is not science. Science has to be based on physical, empirical evidence.
So opinionated, and you're not, okay, like leave it open. We're looking for the graviton, but we're not looking with any intensity for it. And the scale of the force, the weakness of this force compared to the weak force, compared to electromagnetism, compared to the strong force, in a scale, it's by far the smallest. So it's the most difficult to find. Instead of just always declaring in a Popperesque manner, this is not science. Keep your mind open.
I agree with you, Victor.
Remain in a state of inquiry.
Victor, I agree with you. We should explore all theoretical possibilities. But until we find empirical evidence, it is not it is hypothesis. Or worse, it's science fiction.
Of course it's hypothesis.
I think that's the majority opinion.
Of course it's hypothesis.
Oh, no, but you have physicists who talk about the graviton like it's been discovered.
For every crazy idea, you can find a bunch of people that believe it.
What if gravity is not a quantum theory? Did anybody ever consider that? Because
Freeman
by
Dyson
the way, we have a
navigated that.
non-quantum theory of gravity that works pretty well.
I think all is well in the business. To
Gravity-
try to like not break a new record of longevity here, can we
I think people
just wrap up maybe?
checks left and right.
Was that?
Give the $1 million, give the strength people $1 million. The problem is just making people fight for funding, right? Like,
Oh yeah.
Yeah.
Like I said, it's all political, and the string theorists are
Not all
winning
political.
out, and that is going to be the death of physics.
Winning out over whom?
Did you hear what
Condensed
Matthew
matter
said? It's
physics?
about funding. The string theorists are getting the funding because they come up with the most fantastical, ridiculous, they're like wormholes and multiverses, and people believe this
And
crap.
most people that try to do string theory are not able to find a job because there's not enough funding.
Really? Well, go visit.
Yeah, really.
Go visit Columbia University or Stanford University. They get the most fun. The string
Yes,
theory departments
same is
get the
true
most
there.
funding.
pointed out that
Most graduate students
And this
that are
is gonna
focused
be the
on
death
string
of
theory coming out of
physics.
Columbia are not going to become professors because there aren't enough positions.
yeah, it's
They're
true.
going to end up becoming data scientists.
And the glory days of string theory are like kind of,
Past.
someone pointed this out. Was it you, Victor? Like
Yes.
the height of like this sort of like string theory is going to solve everything extended from basically like the late 80s to like maybe the early 2000s.
Yeah, and string
Exactly.
theorists believe they have solved everything, and they're
Exactly.
wrong.
You know, those people are still around, but like, and the results that they found are like incorporated into everything.
Yeah, but tell that to Brian Greene that he doesn't have influence. Brian Greene, who is probably less intelligent than any of us, runs the most important physics department at Columbia University. Why? Because he's a
I think they only have
popularist.
one.
He's a popularist. He's been on PBS. His wife is a movie producer, for God's sake. So this is why he gets the
Take
funding.
it easy, Michael.
And this
Take
is
it easy.
destroying real
No, but I know in
physics.
he doesn't get that much funding. I know in particular that the
Most
process of
important
people trying to
physics
become
department at
his
Columbia.
student in graduate school, he doesn't have a large group. You know,
Oh, but he gets the most funding.
Take Lenny
from book sales, probably.
take Leonard.
And Susskind?
From
Susskind
book
at
sales.
Stanford?
Yeah, so for example, he's one of the originators of string theory, right?
Yeah.
But if you look at like the work that he's been doing over the last 20 years, like with all his PhDs and like all the people there, string theory almost never appears in it. It's all about tensor networks. It's all
Who's
about,
that? Susskind?
yeah,
Yeah.
it's all about, you know,
A
thinking.
lot of string theory.
That's what I'm saying. If you look at the papers he's published over the last 20 years, it's like they use the lessons they've learned in the 90s about holographic duality and so forth. But now the language that they talk in is entirely in terms of like quantum computational complexity, quantum circuits, quantum computers, like tensor networks, you know, all this stuff. Like they don't make any of their arguments depend on the string theory part of it. Like they themselves have moved on. Like they've learned their lessons from it, and now they're using like this whole other set of techniques, which often involve using, you know, fancy kinds of like, you know, basically like neural networks to like decompose high dimensional quantum states into like, you know, these networks that you can show have certain properties and so forth. So, I mean, sometimes they'll still talk about the strings, obviously, you know, and it's just, the field has matured very, very far from the days when string theory was the dog.
Yeah, I think as you say that the role of cosmology
String theory.
has emerged. The role of the interplay of cosmology and particle physics wasn't so enormous back in the 80s and 90s when string theory was on its own so exciting. But that interplay now makes it so that you can't be a serious physicist if you're only doing string theory and you're not thinking about the cosmic microwave background radiation, things like that. So, and then Susskind is doing that.
Yeah, like I think the hype has died down and people have like a sort of, you know, more equanimity.
Also, as like a sounding thing, like, oh, he does string theory. It's kind of like the classic super genius thing to work on. But that kind of like the novelty of that phrase.
Does anybody believe in the phlogiston theory? Does anybody believe in the phlogiston theory? That was very popular a couple of 100 years ago.
Well, but like, I want to make another point too, which is when I was at this Loop Quantum Gravity conference, like there were
lighter
there, like not a lot of them, but they like invited string theorists to have talks and stuff. And like at some of the strings conferences, there's like loop people. So, I mean, decades ago, or however long it was ago, like Lee Smoley, writes a book about, the string theorists make fun of us for doing lukewarm gravity, but like our, theory has some good features too, or whatever. And that book became like a bestseller or whatever. Like subsequent to that, like the two communities kind of like talk to each other, like they go to each other's conferences. I mean, it's not, nobody these days has like a very like.
And Matt, where's the empirical evidence for either loop quantum gravity
Well,
or string theory? Where's the empirical evidence?
You don't need empirical evidence to motivate certain math projects.
Okay.
No, I'm saying for string theory and a lot of related stuff.
Of course not, because
that
they're
has a
not
heavy
science.
presence in math.
They're not science, they're math.
Oh, stop, Michael.
They're not science, they're math.
Before we found the neutrino, where was the empirical evidence? Before we found the
Victor,
neutron, where was the empirical evidence? Before we found...
I didn't say we shouldn't look for it. Of course we should look for it, and we should try to verify string theory if we could. That would be great. But until we do, it's a hypothesis. It's not science.
No, but listen for a second. I mean, in terms of the dynamic of the discussion, I am not always the calmest person in the world. I become animated. I become over animated at times. But Michael, you make it nearly impossible at times for a dialogue to take place because you keep raising your voice. You keep being highly opinionated. You keep denying things rather than being open-minded. And the result is that others, just in order to speak, have to raise their voice, and because I tend to be animated, I then will go off and then have Michael Fishbein accurately say to me, Victor, you're raising your voice. So I mean, just try to be a little calmer so as to facilitate genuine dialogue.
I apologize. It's probably because I'm too close to my laptop. The point I'm making is that we have to make the distinction between a mathematical hypothesis and a science which is based on empirical evidence. And I'm not saying we should not make mathematical hypotheses. Yes, we certainly should, but they have to be tested empirically. And until there's empirical evidence, it is not science.
I think a lot of work that goes on in the field is actually done by pure mathematicians or by collaboration between mathematical physicists. I mean, like, what about the term itself, mathematical physics? That's a valid profession, and things become interesting because you can go in either direction. Okay, this doesn't speak to any kind of physical theory that with known experimental support, but it's interesting mathematically, so you can continue to pursue it. And I think a lot of the work is like that. So it's kind of, and again, it's getting so small funding that I don't think it's like there's a more important project that's being delayed because anyone's doing this kind of research. I think it's.
So do you guys believe in wormholes and multiverses and all this stuff that not only has not been empirically tested, but cannot be empirically tested? And that they call science?
Well,
I call that science fiction.
Well, we've seen that a wormhole is no stranger than quantum teleportation.
A wormhole is what?
A wormhole is no stranger than quantum teleportation.
Well, I may say that knowing that last time I was part of the activity here, 8 o'clock came around and you guys didn't really slow down as far as I was seeing. And so I checked out. And so I'm going to check out. I was going to throw one last thought in before I exit, which is that it seems to be a natural sort of view to emerge based on what Matt, you were showing with the you could put the cut here and you put the cut here, is the is the Feynman sum of all histories view, which is kind of makes it almost quantitative, the way to consider, was it this path, was it that path, that all possible paths, you multiply them by the precisely calculable probability and you sum them up, and then that's the probability of the outcome.
But that's a mathematical calculation. That is not what takes place in the real universe.
There's no calculation that's not a mathematical calculation.
Well, right, because we are limited by something that we invented called math.
As far as what is a model and what is reality, it's never going to be a completed discussion. But I'm saying
a model is only good, approximately good. We have no exact model. And you're right, Feynman's QED is the most exact physical theory we've ever come up with, accurate to 13 decimal places or something like that, it's still not 100% accurate because nature doesn't really give a
But the
damn.
view in general that whenever you're in a position to ask, did this happen or did that happen that led to this observable outcome? The at least mathematically the correct answer that you'll get it by saying everything that could have happened with a corresponding weight of probability for that trajectory.
And do you
and
actually,
then you'll always get a good answer that way.
do you actually believe that that's the way nature works? Come on.
I don't know what it means to say that nature works, and I don't think Feynman ever claimed that he thought it.
I don't think
Feynman idea either. He says that he used to talk in terms of gear wheels. He said, "Yeah, you're never going to find an explanation in terms of gear wheels." But
I'm not sure if I know how nature works, but this is Matthew's session, and I'm getting a sense of how Matthew works. And I just wanted to say that your little presentation about psychophysics there, which was purely narrative, which had none of the intricacies of your Python programming or the mathematical model that you're trying to build or your visualizations, etc. It was excellent in terms of it added another layer to your presentation skills. You know, fill out your damn form for for Stanford, MIT, Princeton, and Harvard, and get going, kiddo.
Or you could be like Freeman Dyson, who never got a PhD, and just sort of start publishing.
I didn't even.
Or collaborate and whatever.
I met Freeman Dyson. He had the personality of a dish rag.
No, we love you.
You must have some pretty interesting dish rags in your house.
He really, he's a very introverted.
His dish rag was spherical. His dish rag was spherical.
Say what?
His dish rag was spherical.
Yeah, he had some pretty good jokes written on the dish rag, but he didn't even laugh at them.
You guys know about the Web of Stories?
Oh yeah,
right?
I love that.
It's awesome, and I think Freeman Dyson's interview is one of the best. Even though the guy who's interviewing keeps coughing, kind of like isn't very annoying, but Freeman Dyson has like this vivid recollection of everything that's ever happened. It seems, and it's so clear. Yeah, but everyone should really check that out. Web of Stories. It got Francis Crick life story. I mean, a bunch of people.
By the way, you should know Freeman Dyson did not believe in global warming. He was one of these guys.
I know that
was on the warpath. And you talk about Crick. Crick was fired from his last position because of racist comments against African Americans. And Francis Collins believes in God with no explanation.
Well, they also had Murray Gell-Mann. And
Gell-Mann did not.
I'm sure there's somebody in there that you'll. They had the guy who did the sound direction for The Godfather, so maybe you'll like that. But there's something for everyone. Web of Stories.
So true. All right, well, that's a good note to end on. Thank you guys all for coming.
Thank you, Matthew.
Next time we'll talk a little bit about the loops, a little about angular momentum conservation, and hope to see you next week.
Yeah, thanks, Matt, and thanks for making a special email about the the Xavier
sure thing
transcript.
Michael Fine, I'm sorry about raising my voice. Sorry about that.
No. I don't recall being critical towards you. I'm sorry if I sounded like I was.
Wherein you were right. I was fighting to get in with. It was the chin to chin thing between Michael and me, and so it let.
No need to apologize, and I don't recall finding anything wrong with your performance tonight. All right. Anyway, thanks for the sentiment.
I apologize for all of us. I apologize for everybody.
I accept it.
On your behalf,
except myself. I'm not sure about myself. I reserve judgment on myself, but I apologize for Victor, Jamie, everybody. Have a good one.
Good night.
Until next time. Bye-bye.
See ya.